Um, Good morning. Thank you all for joining me here on the last day of the conference. I know we've got all kinds of crazy weather going on right now. Definitely looking out west, it's a beautiful sight to the mountains, but I know there are lots of travel concerns, which I totally get. I don't know if I'll be making it home tonight. You're probably in the same boat. But again, thank you for coming and joining me here today. For the next couple of hours, we're going to be talking about all of the best workflows for successful drone programs, all of the different, doing our best to cover from a pretty high level everything related to drone surveying and drone mapping and that sort of stuff. And so that means we've got a couple of objectives of what I'm trying to teach and what I'm trying to share with you today. And really, in summary, that's going to be about the most important things that we've learned over the last 8 years of drone surveying. That means we're going to talk about all the things that drones are capable of, what they can do. And arguably more important, I'm going to talk a lot about what drones should do. And that means I'm going to do a lot of things telling you places where you really shouldn't be using drones or ways not to use drones. Because so much of the promise of using drones and drone surveying is that it's going to be better, faster, cheaper, right? I mean, that's what all technologies are supposed to do. They're supposed to be better than the way things were, faster and cheaper and all of that stuff. But in reality, a lot of drone programs have come to be like, okay, well, you spend less time in the field, but it's a really expensive drone. It requires tons of training. You only use it on specific projects. Doesn't necessarily save money, but the data is pretty cool and that sort of thing. And drones absolutely can be more than that, and that's what we're talking about today. We're talking about what drones actually should do. We'll talk a little bit about also what the right drone is and the right drone for you, where and how you can fly, and of course, how to process the data, because that is going to be one of the most important parts is on the data processing side. As I go through this, that's pretty loud. I wonder if there's a turn this microphone down. But as I go through all of this, I know it's a big room and everything, but I actually really like questions. I like to make this as interactive as possible. So please do raise your hands when you have questions throughout all of this. I like learning from you guys and the questions you have as much as you're here to learn from me and learn a bit more about drone surveying. So please do speak up, raise your hand. If I can't see you, throw something at me. That won't hurt my feelings. A little bit about me. I am the CEO and lead photogrammetrist at Aerotas. I have a formal background in finance and statistics, actually, before moving over into photogrammetry and surveying. I'm a certified mapping scientist with the ASPRS. And the company that I work with, Aerotas, we do drone data processing for surveyors, and we've been doing it since about 2014, which is always a little interesting because in the world of drone and drone-related companies, we are very, very old, having been around and been working for surveyors for about 8 years. Even though in the world of survey, we're a very young company that, there are companies around here that are celebrating 50, 80 plus years in the business, which is pretty cool. But for drones, we've been around for a really long time and something that I'm very, very proud about. All right, so what my goal is today, and I know I've given a couple other talks, whether about, specifically RTK or specifically the drone hardware, and my goal is not going to be any different. My goal is the same in those programs and this, and that is to help you build a drone program, which obviously starts if you help you build one, whether you're starting from complete scratch and you don't have a drone, or whether you have lots of drones and drone experience and you're looking to build it better to make it more efficient, more cost effective, get better data, all of that. But build a drone program that you will actually use. This is the trickiest part here that I kind of breaks my heart as someone that really likes drones and loves the technology and knows the promise about all of it. There are lots of drone programs where people will buy really, really cool, really fancy high-end hardware, and then they don't use it because it's too challenging, either from an operational standpoint or a workflow standpoint or a data processing standpoint or any of that. They don't use it. And that's a real bummer to me. That's not a good drone program. A good drone program is one that you will use. A good drone program is also one that saves you time. This is another very, very common pitfall. People buy these really nice drones. They collect all of this data. They're, what would have taken multiple days in the field, they can gather in just a couple of hours. And then all of a sudden they're spending days or weeks in the office trying to process all of that data. That doesn't actually save you time. I mean, it might save your field crews time, but if you're just moving all of that work into a larger, more expensive pool of labor in the office, that doesn't save you any time at all. And also one that gets better data. All of that stuff is great, but if you get, junky, low accuracy data that's, no better than Google Earth, that's not helping anyone. So we're going to get you better data as well. And Really, the most important way to do this is not, a lot of people come in expecting, I'm going to tell you, do X, Y, and Z, and you're going to have a really successful drone program. But almost as important is kind of all of the don'ts of drone surveying, avoiding all of the pitfalls that are out there, the ways that you can try and do something that winds up actually eating away all of your time and eating away your money. So a lot of what I'm going to be talking about today, like I said, is the don'ts of drone surveying. The things that we've learned are the common mistakes and pitfalls that people make. That means don't use the wrong tool for the job. There are a lot of different drones out there, and outside of the world of drones, there are a lot of survey tools. And a lot of times, drones aren't the right tool for the job. And even when you have a drone, not every drone is the right tool for the job. If you have an awesome LiDAR drone, that's fantastic. LiDAR is great for running topo in vegetated areas. But if you're doing stockpiles or ALTA surveys, let's pick an ALTA survey, for example, a LiDAR drone is a massive pain in the butt for an ALTA survey. If you're trying to draft parking stalls or something like that, and all you have is a LiDAR point cloud, then actually drafting the paint striping, you can do it with LiDAR, but it's a pain in the butt. That's much more easy to do with photogrammetry and with imagery data, where you can see all of the paint striping clearly, you can see utility access panels, manholes, and things like that. So being able to pick the right tool for the job. Even in here, I say, obviously, things that are outside of drones. GPS, right? Traditional GPS, a total station. Flying an airplane. There are manned aerial companies in the exhibit hall this week, and they are still around because there's still a place for them, right? If you are doing anything north of 500 acres, usually consider that sort of thing. But there's a place for all of these different tools. A lot of other don'ts is don't overspend on gear you don't need. And I say this as a technical enthusiast myself, someone that really likes a lot of cool technology. People want to buy the latest and greatest technology because it's the latest and greatest. And that's kind of fun. I like that too, right? I have cool new drones that I take pictures with my family. I have very high-end computers because I love computers and things like that. But a lot of them are not going to be a good business decision, right? Buying a $10,000, fancy server-grade multi-Xeon processor computer is really cool, but that's not going to be what actually makes a successful drone program and makes it profitable. Same thing with the actual hardware itself. There is absolutely drone LiDAR systems well in excess of a few $100,000 and up from there, and they might get marginally better data and work marginally better in certain circumstances, but those ones are very, very hard to ever make a successful drone program out of, just because it costs so darn much money. You're almost never going to get an ROI on it. And what I've learned from being in this business long enough is if you don't actually get an ROI on it, the program doesn't last. You might have the drone for a while, fly it for a year or a couple of years, and then by the time you need new parts or upgrades or new training, or the pilot leaves, they don't refresh the drone program. They don't hire a new pilot. They don't train one. They don't buy a new drone because they said, well, that was a cool experiment. We spent a ton of money and didn't make it back. We're not doing it again and going back to the old one. But don't overspend on gear you don't need. That's going to be pretty darn important. Don't spend too much time in the office. I mentioned that earlier, that's another big pitfall where people spend huge amounts of time processing the data. What I say here is get the data you need and then get out. We're going to cover that a lot as well, of making sure before the whole project even starts, know what data you're trying to get out of it. If you're just trying to get topo, then it makes no sense to try and classify power lines and get your photogrammetric model to model the tops of power poles correctly. That's a waste of time. You should focus on topo, get just topo, and get the heck out. Likewise, if you're just doing a 2D ALTA, who cares about topo? Or don't worry about that later. Get your 2D planimetrics, and that's it. And then get out of there. That's going to save you a huge amount of time. And lastly, don't treat this like a research project. A good drone program is boring, repeatable, and efficient. And that's one of the weirdest parts about this, that I come up here, admittedly, as a technology enthusiast, someone that has been working in drones for as long as drones have really been around on the consumer stage, someone that has been working, building, buying my own computers and things like that. And my goal is to make this as boring as possible. I take this really cool technology that a lot of people, you can go to, kids in school and say, hey, you want a career in flying robots with lasers strapped to them? Yeah, get the kids excited in a school program. And that's fun. But then I talk to surveyors And I'm like, no, you want the shine to wear off of this program so quickly. You want your drone to be dusty, dirty, and just work. And your field crews pick it up in the morning, go to a job site, put in a battery, push go, and it's just part of the job. It's just boring and uneventful. And that to me is the real success of a drone program. It's when you can take all of this and just make it boring. It shouldn't require a lot of these crazy PhD level analyses. I've done a lot of those. They're hugely time consuming. And again, like those other programs, they just don't last. So to actually make it boring, what we found with most surveyors, with most companies in general, is there's kind of a journey that a lot of people go through as they learn drones. And this is something that I really probably should update, as drones are becoming a lot more mature as a technology too, which is really, really cool that we've been figuring out what drones are good at. We've been figuring out what drones aren't good at. What are the good workflows? What are the challenging workflows? And people are now starting at kind of different points along that, because you can start and buy a $40,000 drone with some reasonable level of confidence that it can actually get you good data. Doesn't mean your workflow will get you good data out of that, but you can start with that. The way that it used to work, though, is everyone would start with just buying a drone for basic photos and videos. Hey, it's a cheap one. I don't want to invest too much. Maybe spend a couple $100 or $1,000 or something on a photo drone or a video drone. Those are actually still great for photos and videos. There are lots of, most drones in the world are actually designed for taking photos and TikTok videos and that sort of thing. Then they'll start throwing it in the software, whether it's Pix4D or Drone Deploy, something like that, start making ortho photos out of them and say, wow, that's cool. We can maybe do some basic mapping. Then you start integrating your GPS, you start integrating your ground control points, maybe RTK to get some accuracy, some precision in there. Then you start working in 3D data as well, exporting it into point clouds, seeing what you can vectorize, seeing what curb lines look like and how to draft those. Then eventually getting it all into CAD, working it together, working those then into the data of your final survey deliverable. But at the real top of the pyramid, the end of this journey is when you make that into a repeatable workflow. That's the real boring side of this, because this whole kind of blue base of the pyramid is honestly not that difficult to do it once. The first time you do it, even the second time you do it, is not that difficult. The challenging part is kind of the 5th and 10th time you do it, when it's no longer a research project. Your goal is to just get it done quickly, and make sure that you do save time and money on it. And here's the high-level workflow that we're going to be going through today. And this has really been refined and enhanced over the years. It's always been a fairly similar workflow for us, but we've added a few steps, taken away a few others, kind of merged them because we've learned more and the technology has changed. But the beginning has always stayed the same for us. The beginning of any drone workflow, and this is the workflow once you actually even have bought the drone. I'll cover the drone hardware in a little bit, and all of that set up for the program itself. But the actual workflow for gathering and processing the data always starts in the same place, which is mission planning. Mission planning is super boring, really quick, but very easy to forget. Think of this as like your packing checklist, right? Whenever you go on a trip, you have a packing checklist and just make sure, okay, yep, I've got socks, underwear, pants, shirts, whatever, toiletry kit, whatever. It's pretty boring, but it's pretty important, because if you go on a trip and you don't have any of those things, you're going to kind of be in trouble. Not the end of the world, but it's a real pain in the butt if you travel somewhere and don't have any socks. Same thing kind of with the drone. You should have your mission checklist. Just say, okay, let's see, make sure my batteries are in the case and charge. I plan my mission. I check the weather, and okay, we're good to go. It's all it is. It's a really kind of boring thing, and we'll cover it a lot, but that's one of the biggest time savers when it comes to workflows. Is taking that 2 minutes the day before, or maybe even a couple days before, just to say, all right, where am I flying? Where are the targets going to be, and how are we going to do this? Now, I say just a couple of minutes because mission planning is another one of those things that actually is really easy to do to overkill as well. People want to take a mission and say, all right, we need everything set up perfectly. Here's our 2-week process for planning the mission, for who's going to set the ground control. It's going to be set 2 weeks in advance. It's going to be marked with these permanent targets, and we're going to fly at this altitude on this day and this time. And honestly, it doesn't need to be that intense. That also can be a time killer. But mission planning, we'll go over all the steps in that. It really should be 5-10 minute process or something to actually plan a mission. That's all it takes for the majority of missions. There are some exceptions. We'll talk about that too. Going into data collection, that's going to be actually out in the field collecting your data. That's both drone data, but also RTK, GPS data, as well as all of your ground data, ground control points, any ground shots, things like that. Flying the drone as part of data collection is the most boring, easy part of all of this. Drones nowadays are, once you should be planning the mission in the office, probably. You can plan a mission in the field, but we recommend, when you do your mission planning, it really should just be drawing a box of your area of interest and setting a flight altitude. That's about all that creating the mission is. And when you go out in the field, you should set up the drone and push fly. If it's more complicated than that, then there's a lot of room for improvement for your actual data collection and flight side and flight operation. And then point cloud processing, that's one that we've renamed because it's no longer photogrammetry. Photogrammetry remains the most common way to process data and to process and create drone data. But now it's not just photogrammetry, it's photogrammetry and LiDAR are both becoming much more common. LiDAR, as I've mentioned in my other talks, LiDAR remains less popular than photogrammetry right now, and that's actually a good thing. Photogrammetry is a lot cheaper, it's more proven, it's a more robust, reliable workflow, whereas LiDAR drones cost 3, 4, 5 times as much or more. The data is more intensive and time-consuming to process, and it's just generally a little bit more of a pain in the butt. I love LiDAR data, we process a lot of it, but it is a bit more of a pain in the butt. And merging it with photogrammetry, creating all of these point clouds, creating those 3D models, those rich, high-resolution 3D models, is more than just photogrammetry processing nowadays. And then in here, after you create all of your point clouds, is accuracy verification. That's a really, really, really important step, and we think that location for accuracy verification is a really important place in the workflow to actually do it. That's another what should be a very quick step that is often overlooked and will sink huge amounts of time if you don't do it until later. We'll talk exactly what I mean about accuracy verification, but that's basically just saying, hey, make sure that the point clouds that you created, the surface you created, just make sure that it lines up with all of your other data, right? That your topo shots are accurate, that your break lines and planimetrics, your 2D like geolocation is where it's all supposed to be. Because if you start doing a whole bunch of drafting work and we're getting it all into CAD and all of this other work before you do your accuracy verification, sometimes we've seen people spend 8, 12, 16 hours on a project drafting it, getting all of this data extracted, only to find out later that it was inaccurate, that they had done some of the photogrammetry modeling wrong, they'd done the LiDAR processing wrong, and they kind of have to throw a lot of it out or find creative ways to shift it accordingly. So accuracy verification is kind of like mission planning. It's a really, really small, fast step when you do it right, but it's really important to save you a bunch of time down the line. Line work drafting is taking those rich 3D models and actually creating planimetrics, creating a more lightweight surface. It's often called vectorization, or basically just reducing those rich 3D models into something that's smaller, that's more easy to use, that can be used in CAD. And then getting that final thing into CAD, all of that data into CAD, creating your tin surface, adding your break lines, adding your symbols, and making sure that all of your layers are correct in there. That's the last step. Because when you put everything together, what you are looking for is just a survey. Or more specifically, what your clients are looking for is a survey. Very few people say, I would like a drone survey, at least from the client's perspective. What they often say is, I want a survey. And oftentimes the people that are saying they want a drone survey really are only saying that. That's what we see, what we hear from engineers a lot of times, is that they want a drone survey because they want the live up-to-date imagery. They don't actually care what technology was used to create the contours or the planimetrics or what you used to take the shots, because they want to get a survey. And a final survey, when it's done with a drone or whether it's done with something else, should look exactly the same, whether it was done conventionally or with a drone, and the drone might look a little better. Yes, questions. Thank you. Yeah, so you're saying for like the drip lines of the buildings and how those actually are ortho-rectified on the imagery?
Yeah, I mean, a lot of times there's, for
Yes.
And if they were truly orthorectified truth, it would end up with basically a shadow of no image. So a
Yep.
lot of times you just basically have a filter. The group is not necessarily what it's.
Yeah, it's a great question. And yes, drone processing does alleviate that considerably. It's not perfect, and I'll tell you exactly why. So, first, the way that it alleviates it. Traditional aerial photogrammetry was done with very highly calibrated cameras, but typically with much lower overlap. That the amount of overlap from one photo to the next was, by modern digital standards, very, very low. But they could get away with it because they were such highly calibrated cameras. You match a point in two photos with a perfectly calibrated camera, you can be almost perfectly confident that that point is exactly where you want it to be. With drones, the cameras aren't that high quality, which is trade-offs. On the one hand, we wish we had quality cameras, but quality cameras and calibrating cameras is ridiculously expensive. So the way that digital photogrammetry makes up for that is with, by traditional standards, really high overlap. General rules of thumb that the industry has settled on is somewhere between 70-75% side lap, 75% front lap. You do the math backwards, and what that means with 75-75 overlap is any one point on the ground can be seen from 16 different photographs. And that much, much higher level of overlap means that you are seeing the building from the side, you're seeing the building from the top, from the front, from the back, and from the other side. You have a lot more angles to it. And the way that the orthorectification process works with digital photogrammetry is it actually starts not by creating seam lines like you might with traditional photogrammetry, but by creating a point cloud, by matching all of those points. And then the imagery that's orthorectified on top of that is a blend of all of those 16 photos that's orthorectified on top of the point cloud. So it's a slightly different technical process to do that. So what that basically does, it kind of drapes the imagery on top of that 3D point cloud, which will have those sharp building corners. So that's the reason why it gets rid of that kind of that look of leaning buildings from non-perfectly overhead imagery. That said, the reason it is not perfect is because it's draping it over that point cloud. Point clouds are then a series of dots, points. They are not going to be perfect lines along the edge of a building. So what you often see, if you were to zoom in on this photo, for example, you can see here with this building that there's sharp building lines. If you were to zoom in, you would see that the actual edge of the building kind of looks wavy a little bit. Not hugely so. The size of the waves is going to be a couple tenths of a foot or so, but it's not going to be a clean, crisp, perfect line. You can get a clean, crisp, perfect line if you actually go in and put manual break lines in the photogrammetry software before it actually does the orthorectification process. That is ridiculously time consuming and not a workflow that we typically would recommend, but that's one way to get around it. Does that answer your question? Cool. Thank you. I love questions like this. I know, especially on the last day of a conference with weather coming in, answering questions is great. That is a great question. So I believe it actually uses the point cloud directly and then orthorectifies the imagery on top of that. All right. So let's talk about some drone technology, some drone hardware. For those of you that weren't there, I actually gave a talk yesterday specifically on drone technology, which I'm going to cover some of that, but I covered it in much, much more detail yesterday. So if you want, you can shoot me an email and we have a copy of that presentation and a video of that presentation if you want to go in much more depth about all of the hardware side of drones. But for those of you that weren't there, we're going to cover it a little bit just briefly right now. First of all, one of the things that's important with drones is how we do not evaluate drones. Because this is where a lot of those common pitfalls come, people that we think evaluate drones in the wrong way. For example, how many megapixels a camera has. That is great, but a high megapixel camera does not mean that it is going to be a good drone for a total workflow survey. We do care about accuracy. That's an important single component, but saying, hey, that camera has more megapixels, ergo it's better, is completely the wrong way to look at things. The overall quality of the optics, how it integrates with the GPS system, how easy it is to use, whether it's a 50-pound drone that takes 3 days of training or whether it's a 2-pound drone that anyone can use is much more important than things like just how many megapixels. not to mention, a lot of drone manufacturers have gotten really tricky about how they even report megapixels, where they're like, hey, check out this 48 megapixel camera. Or Samsung has a phone now that they say it's like 250 megapixels or something like that. And anyone that actually works in cameras looks at it and it's like, I mean, that you're really stretching the definition of how you even measure this technology. It's not actually that good. It's got some cool tech to it, but it's not actually that good. So megapixels by itself is not the measure that you should be using. Likewise, how powerful the LiDAR sensor is. We've never seen a drone survey where someone said, gosh, if only I had 600,000 pulses per second instead of 250,000 pulses per second, or something like that. These things gather so darn much data with LiDAR sensors that like the number of pulses per second has kind of become negligible. And yet we still see so often people say, oh, the drone has higher pulse count. Therefore, it must get better data on the LiDAR and higher density. And that's not actually the way that LiDAR sensors work nowadays. That's not the bottleneck. The pulse density is not the bottleneck for LiDAR sensors. Yeah, question? Technically, yes. In practice, not really. And the reason I say that is because pulse density has gotten to a point where it's so ridiculously high, especially when you are talking, 400,000 pulses per second, flying at 200 feet. We have seen very, very few cases. We've done actually tests on this as well, where if you double the pulse density, for example, you actually start getting pulses where you weren't before. It's so high that if there's a gap in the vegetation, you'll usually get 10, 20, 100 pulses on the ground. And so if you double the pulse density, you'll get 200, and if you half it, you'll get 50, but you'll still actually see the ground surface. What actually matters a lot more in terms of penetrating particularly dense and tricky vegetation is actually going to be increasing your overlap. That gives you different angles. It gives the LiDAR sensor different opportunities to find gaps in the vegetation and find the ground that way. Increasing the overlap is a far more effective way of increasing the density of points on the ground than increasing the amount of the pure number of pulses per second on LiDAR. Yeah, we do, and I'll actually cover that a little bit. But with LiDAR sensors, our recommendation for overlap on LiDAR sensors is actually quite a bit higher than what most drone manufacturers recommend. A lot of drone manufacturers recommend what we would consider pretty low, in the order of like 30 to 40% LiDAR overlap, swath-to-swath overlap. And we've seen a lot more success from a business and workflow perspective at closer to 60%. And if you do, again, kind of do the math backwards, what that means is that each point on the ground should ideally, if it were a ideal flat terrain, should ideally be covered by 3 swaths. And that gives a huge amount of workflow redundancy, more opportunity to penetrate the vegetation and to find that ground. Now, yes, that does actually take a little bit more time in the field. It does collect a little bit more data. And if you've heard me talk before and hearing me talk today, you will know I am militant about reducing the amount of data that you collect when you don't have to collect too much data. So hopefully that means when we say, yeah, increase your LiDAR overlap, you might actually take my advice on that. So we say about 60% swath-to-swath overlap with LiDAR is a good way to get better quality data to actually increase that vegetation penetration, but also it increases just the overall reliability, right? If you do 35% and a building's in exactly the wrong place, then you kind of get some shadows over the building where the LiDAR didn't actually get the ground surface. You increase the overlap, it reduces those sorts of gaps very, very considerably. So it's a really great question. But all of those, part of what makes it such a fantastic question is that it's not, well, if you had only spent the extra $20,000 on the bigger LiDAR sensor, then you would have gotten the data. No, the extra powerful LiDAR sensor is not going to be able to see through the building. If you're flying through ultra dense vegetation, the way LiDAR works, I don't have it in this presentation, but in my other one, LiDAR doesn't actually see through trees. It cannot see through leaves. It's a common misperception that people think it can actually take a leaf and, the wavelength of the LiDAR can see through it, and that's not how it works. The way LiDAR works is that it just covers it with so many laser pulses that it finds minuscule gaps in between the leaves. And that's what it actually uses to pull back. So a more powerful LiDAR sensor is not able to see through any leaves or anything like that. It might be able to find those gaps from a higher altitude. In fact, that's the biggest thing where a more powerful laser would actually make a difference, is higher altitude. If we take, kind of your like your DJI L1 style laser, you can already see when that gets to about 400 feet, which is as high as you can legally fly drones in the United States. You can see on some surfaces it doesn't catch the reflections back at 400 feet. A more powerful laser would. Now, of course, you don't need that much more powerful because you're not going to be flying at 1,000 feet or something, at least not with the drone or the modern day drones. But if you were on a 1,000-foot drone, that's when, okay, we need to start talking about how powerful the actual laser is, how accurate it is going to be at these longer ranges, and all of the other stuff. The technology that is often sold on drones today for really powerful LiDAR units makes sense if you're going to be flying at 1,000 feet above ground, 2,000, 3,000, 5,000 feet, but is not the bottleneck, is not an issue when you're flying at 200 or 300 feet, which is usually the kind of Goldilocks zone for most drone LiDAR flights at the 200 to 300 foot range. Oh, the speed that the drone flies? Increases it increases the density of points on the ground, but it doesn't increase the penetration. Again, typically penetration is not because of the pulse density, it's because of whether it's actually finding the gaps, the angles, and the leaves. Interestingly, with LiDAR, if it's a particularly challenging, highly vegetated site, one of the things that, again, we don't almost ever recommend with photogrammetry, but does make sense with LiDAR, is doing a double grid flight pattern where you fly once north to south and once east to west, or having two different flight patterns at 90 degrees to each other. And once again, the purpose behind that is it just gives the laser more opportunities to find gaps in that vegetation from more different angles. That's going to be much, much, much more important. So actually, faster but more overlap and more different angles for the drones is going to increase penetration relative to slower but not as much overlap. And that's all on the mission planning side, right? That's not how you evaluate drones, just to finish these slides. But thank you for the question. I appreciate it. I think those are really, really valuable. Same thing, how many minutes of flight the drone has. We've been talking about all this pulse density and that sort of thing, but how many minutes the drone has is often a misleading statistic because it is based on flight altitude, flight speed, the amount of area you can cover, the width of the camera angle of the lens of the LiDAR unit, and that sort of thing. A much more accurate measure of how long a drone can stay in the air or how good it's going to be to you is how many acres of ground can it cover in 30 minutes, in an hour? How many acres does it cover, and at what accuracy is going to be more of the question that I would ask. When I see, this is another one also that drone manufacturers really love to fudge the numbers on these things. They say like, oh, this thing can fly for 50 minutes. It's like, yeah, in a laboratory environment, hovering, not flying laterally, going until it's absolutely 0% battery and the battery dies and the thing just flies out of the air. It's not a real world number. We work in the real world where you have to fly. It has to climb to a couple hundred feet, fly around in wind with a payload, and you don't want to fly until it literally runs out of batteries and drops from the sky. You want to land it with enough battery to make sure that it doesn't crash. I don't think anyone wants to crash their drone. So the minutes of flight time, that shouldn't be what drives you. And yet these are a lot of the statistics that are on the sales sheets when it comes to buying a drone. Look at how many megapixels our camera has. Look at where our lens was built. Look at all of this. And those aren't how we really evaluate things. Likewise, how cool the drone looks, whether it can be used in drone racing or whether or not it has a thermal camera. Thermal camera is another interesting one too, because so many people and their companies and their bosses want I want to buy one drone and that's it, and every single department will use it. And we've just found that's not a great workflow because when no one owns it, then no one winds up using it. Or if everyone does want it, then they have to fight over it, and it becomes operationally inefficient. It's not a problem with the technology. It's not that a drone can't be used for multiple things, but the operational complexity of trying to share assets with different divisions of a company, with different sensors, different users, all of that becomes messy. Not impossible, but definitely messy and kind of tricky. So When it comes to survey, we think drones ought to be bought for survey drones. So for actually how we do evaluate drones, things like accuracy. What's the final accuracy of the product that this drone is able to put out? That's going to be so much more valuable to us than the number of megapixels. Megapixels on a camera does influence that, but camera quality, GPS quality, workflow quality, IMU quality, all of that goes together. Also, total cost of ownership. This is another one where most people look at that first one when they think of the cost of the equipment, and they kind of ignore these last two costs as well. And if you've ever been involved in purchasing or starting a new drone program and actually trying to quantify what the total cost of your drone program is, you know these last two are often going to far exceed the cost of the equipment as well. The cost of operating it, because pilots, people are expensive, labor is expensive, data processing is expensive, both in terms of the labor, the software you have to buy, the hardware you have to buy, all of that stuff. And so drones that, even if the drone is very expensive, that might be worth it. But the problem are drones and drone programs where the operation and data processing side of things blow the cost out of the water. And that's part of why we really like a lot simpler drones and why we see simpler drones more effective in drone programs. As I mentioned earlier, Aerotos, my company, we process data. And so we have a unique view because we get to see the companies that fly their drones. We see them more often because they fly their drones more often. And I can tell you the drones that we see the most are the ones that are the easiest to use because they're the ones that have succeeded in making their drone programs super boring. A drone program where someone takes it as a research program because they love this technology, they want to do it, doesn't get used as often. A drone program where it's just a tool in the truck and it's boring gets used a ton. And that gets into some of these other things that we like to see. Skill required to operate should be low, right? My family's actually involved in classic cars, and so I get to see a lot of cool old classic cars that are extraordinarily challenging to operate. They have all of these knobs on the steering wheels for advancing the spark ignition, all sorts of different stuff that no one could drive today. If anyone's ever driven, an old manual transmission car without synchro mesh or something, it's kind of fun having to rev match an engine when you're a professional at that and when you're actually trained on it. But then when you want to just get to work, a lot of people buy a Prius because it's dumb and boring. And that's what I kind of want drones to be. When they're successful from a business standpoint, the Prius is going to be a lot better of a commuter car than a 1920s Bugatti or something. The Bugatti's awesome, but it's not going to be the boring get you to the airport type car. And that's what we look at. We want to recommend, or at least in this program, I could talk about the fun, crazy side of drones, but that's kind of a different topic because today we want to talk about the Prius, the boring, the get you to work one. Making sure that you care about things like hardware and software support, and like I said, company longevity as well. Being around for 8 years, I've seen a lot of companies come and go. This one, which I talked about before, was a cool concept of a drone that took off vertically, tilts its propellers, flies like a plane, has a good camera. But the company went bankrupt. People that had these drones were stuck with them that didn't have the software support anymore. And they basically kind of lost out on their investment because it just didn't really stick around. So just a couple words of caution when buying drones. Always beware salespeople. There are honest salespeople out there. There are nice, good ones out there, but they're incentivized to often sell you a more expensive drone. I'm a little bit the opposite. You get to hear my perspective today, which I'm incentivized for you to have a cheaper drone that works a little bit better. Do not buy on tech specs alone. That's probably the most important. If I can urge you anything, please, please, please don't buy on tech specs alone. Tech specs are wonderful. Good tech specs often do lead to a good drone, but really it is the entire workflow that matters. Lastly, just talking a little bit about kind of some drones out there. Again, if you really want all of the detail on the different drones in the drone ecosystem, different companies that are out there, generally speaking, there are two categories: DJI, everyone else. DJI is the most common manufacturer. We definitely see most drones that are flown for survey are still DJI. Simple workflow, relatively cheap, easy to use, and very good, but typically, if we're being honest, not the best possible accuracy. With the downsides being that they're Chinese made, poor hardware support, and they're not going to be the most cutting edge technology. They're not, if you buy on the tech specs, like I've said before, DJI will lose out, so to speak, on the tech specs because other people will put more powerful LiDAR sensors, cameras with more megapixels on their drones. And the kind of everyone else categories are more specialized. They're often, not always, made or in some ways assembled in the USA, better hardware support and more cutting edge technology, but they really have a much more complex field workflow. They're much more expensive and they require specialized training. And I'd caution you to not underestimate how important these complex field workflows are. As far as the options for DJI drones out there, this slide's actually just a little bit old. I should have updated it with one from that I talked about yesterday. The Phantom series is being quietly discontinued by DJI. It's been the absolute workhorse for most drone surveying missions for about the last 4 or 5 years because they have been quite affordable, really, really easy to use, small, unobtrusive, and they just work. They've just become so boring and they work. And that's why so many surveyors have been using them successfully. The latest model, which I have a slide later down a little bit later, is what's called the Mavic 3 Enterprise RTK. That is the successor to the Phantom 4 RTK. If anyone likes the Phantom 4 RTK, you'll like the Mavic 3 Enterprise RTK. Naming convention is crazy. But the more powerful DJI drones are going to be the M300. That's their larger modular, 30-pound multi-rotor and that sort of thing. So those are your main DJI drones, but a lot of people don't want DJI drones because they are a Chinese manufacturer, and that's obviously in the news a lot lately. And I want to address at least a couple of things about that make it really, really challenging, because I've gotten a number of questions this week about, oh, well, I don't want to buy a DJI drone or that sort of thing, or are DJI drones going to be banned? Which, a few years ago would be a completely crazy question, but there are people talking about that, and I just kind of want to address the political side as best as I can here, that obviously there are tensions with DJI, with China geopolitically as well. There's no credible information that DJI drones will get banned or that Chinese drones will get banned. And the real challenge with that is that we live in such a globally interconnected supply chain that pretty much all drones have at least some level of Chinese parts in there. And in fact, that goes to, my next question is, people say, I don't want to fly DJI or I want something that's not Chinese. The question is, how non-Chinese is non-Chinese enough? Which sounds like an absurd thing to actually be talking about now, but you kind of need to worry about it, right? DJI is the biggest company, and some people say, oh, well, I want to buy an Autel drone because it's not DJI. And honestly, Autel, it's still a Chinese company. It's still manufactured in China, and it's still basically 100% Chinese. It's a perfectly capable drone, and I have the next slide is actually about that, but it's still Chinese. Things like the Rock Robotics sensors or something, a popular, well-marketed kind of LiDAR sensor, is usually still on a DJI airframe. If you look at some of these other ones that even say like assembled in the USA, something like a FreeFly drone, most of the overwhelming majority of the parts and chips and controllers are still made in China. Question? No, so it's a great question, and the devil's in the details. What does it mean by ban, and what does it mean by Chinese technology? When they say ban it, sometimes, for example, let's take DJI. DJI drones are banned by the Department of Defense. That totally makes sense. I think that is a great policy that United States military should not be flying DJI drones, and they don't. However, if you are a surveyor that has been contracted by the Army Corps of Engineers for an Army Corps of Engineer project, are you allowed to use a DJI drone? And the answer then gets really muddy, and it often depends. Because as a surveyor, you are not banned from using DJI drones, certainly, or any Chinese drones or anything right now. And when you're working for the Army Corps, it depends on the project. And we've actually done a lot of these projects. I can tell you the answer is for certain projects, yeah, you absolutely can. If you're just doing a survey of a river basin to make sure that it doesn't flood during the next wet season, the Army Corps will usually say, we do not care what drone you fly, go ahead, even though you are working for the Army Corps, which itself is not allowed to fly DJI drones. If, however, you are doing a survey of a munition site on an Air Force base, they're going to say, what drone are you using? It better not have any Chinese tech on it whatsoever, and you are going to be limited to some of the most restrictive DoD different policies and procedures out there. I forget exactly the acronyms of the highest tier of military spec restriction, but you're basically flying these like Lockheed Martin style multi-rotors, which do exist. They're not common in the survey world because they're ridiculously expensive and ridiculously challenging to use and require huge amounts of training to use them properly. But there's also then everywhere in between. There are some municipalities out there, state water districts, where, again, the state says, okay, you as a state may not use DJI drones, but they're okay with Autel drones, even though they are equally Chinese made and equally Chinese owned at 100%. And then there are same water districts where they cannot operate it, but if they contract to a surveyor, the surveyor can use whatever they want. It gets ugly and messy because, again, if you say just no Chinese technology, well, throw away your iPhone because that's made in China too. It's just hard. And don't get me wrong, I so wish there was, a company that like Ford, that made a drone that was survey capable. And there just isn't one out there right now. There are companies that actually are made in the United States. Yeah, question. No, they don't. DJI's ability, or DJI's geofencing, yeah, that's another interesting thing. That they have multiple tiers of where you can and can't fly based on unlocking. You can unlock everything with DJI. Knowing the background with it, they implemented that system basically out of political pressure, with Congress basically saying we don't want drones flying near airports. You need to lock it down. If we're talking from a business standpoint, that's actually pretty easy to unlock a lot of these things. They have most of those tiers. Most airspace is open. Then they have these escalating tiers where check a box. Yes, I'm okay to fly. Or check a box and enter your name so that they know who it is when you're flying close to the airport. And then there's actually like on airport properties or on federal prison facilities or some of the more restrictive areas. Those ones require to actually submit a day or two in advance to actually prove that you have authorization to fly there. We've found in the real world that's not a really big hurdle to jump. And in fact, it's in some ways kind of responsible because it helps you, it prevents you from getting in trouble without realizing it. Because there are a lot of times, like when you're doing a survey on a job site, you don't look at what's going to be a couple, blocks in the other direction. And if it's a federal prison facility and you accidentally flew a drone over a federal prison facility, you could actually get in trouble for that. And then DJI geofencing actually kind of helps prevent those sorts of things, which isn't too terrible. But to get back to these drones, some of them actually do have geofencing as well. Yeah. They have the most robust, partly because they are the biggest company out there. And that means they get the most attention out there. Realistically, if let's hypothetically say that Autel or something does become wildly successful, as big as DJI, I can pretty much guarantee that they will then be forced to put in the geofencing as well, just from political pressures. But yeah, I wish there were more drones out there. Skydio is a company that's, just for those of you that are interested in kind of the future of drones, Skydio is a very interesting drone company worth looking at. They are actually American made, or mostly American made, closer to the fully American side. They just don't have a good survey capable drone right now. So I can't recommend them for any sort of surveying drones, but they're a very interesting company worth looking at that I hope can actually manufacture survey capable drones. Right now, their whole focus is on public safety, like police departments and search and rescue things and certain military operations, that sort of thing. I do want to talk about the Autel Evo 2 RTK just specifically. That's a very common one because its main benefit is that it isn't made by DJI. That's the #1 reason why people recommend the Autel Evo 2 RTK. Like I said, Autel is still a Chinese company. It's still made in Guangzhou or Shenzhen. I'm not entirely sure, one of those places. Still made in China by a Chinese company. And it has a linear rolling shutter and just a smaller image sensor that hurts it relative to the Mavic 3 RTK. So if I had to say between the two drones, the Autel Evo 2 RTK and the Mavic 3 Enterprise, the Mavic is just a little bit better in pretty much every way. The Autel Evo 2 is a perfectly capable survey grade drone. It's completely usable and it can get good data, but it's just not quite as good. It's not everything that everyone cracks it up to be. That it's not made in America. It's not going to replace the Mavic 3. It's just not quite as easy to use in our opinion. It still works. If you have it, if you use one of those, perfectly competent. It absolutely can be used. But if you're deciding between them, yeah, we still think the DJI is going to be a much better value overall and a little bit, a lot easier to use and a little bit better data quality. Just kind of getting through all of this. Airframe types, small all-in-one multi-rotors like the Phantom, like the Mavic series. These are the ones that are overwhelmingly the most common drones out there for surveying. And again, that goes back to the workflow side of things because they're just straight up easy to use. They're easy to transport, which is a very underappreciated aspect of drones. It's something that your field crews aren't going to look at and say, well, that's a pain in the ass. I don't want to load that in the truck. M300 and a lot of these bigger ones, micro drones, things like that, field crews look at that and say, I don't want to use that thing. It's a pain in the butt. They will use it, but they're much more excited about things like Phantoms and Mavics because they're so much easier to fly, so much easier to set up and unload, so much less intrusive in the sky. Those are great. And then fixed wings and VTOLs, vertical takeoff and landing drones, have very much fallen out of favor lately because they used to be common when drone battery life, when drone longevity wasn't as good. Now that multi-rotors have really improved their aerodynamics a lot over the last 5 or 6 years, they've improved their battery, the manufacturing quality, how lightweight they are. People have realized that small multi-rotors are just as capable of multi-hundred-acre sites as fixed-wing drones are nowadays. Sure, a fixed-wing can fly a, call it a 1,000-acre site in like 2 flight batteries or something, and the small multi-rotor might take 5 or 6. It's actually not that much of a time difference because they're flying at about the same speed. And the multi-rotor, you just come back, change a battery, and put it back in. The advantages of the fixed wings in the current world of drone surveying are kind of negligible. You're also very limited in terms of just regulations, right? And radio signals. You can't fly a 30-mile drone, a 30-mile linear site with a single drone from a single takeoff place. That's not a technological limitation. It's not because of the batteries or anything. It's because of the regulations. So if, in terms of regulations and wireless technology, you were allowed to fly a 30-mile site by just letting the fixed wing fly the whole thing, then yeah, a fixed wing would have huge, huge benefits over a small multi-rotor. But in today's current environment, the multi-rotors are far, far, far more flexible, more cost-effective, and easier to use than the fixed wings as well. Talking a little bit more about GPS workflow options as well. This is another one that was another talk that I gave, was very in-depth about GNSS processing workflows, how you actually connect an RTK drone to a base station. Typically modern day drones, and in fact, by our recommendation, every survey drone that you buy today should be RTK enabled. There are older drones that are non-RTK enabled, like your old Phantom 4 B2 series or some of the Mavic series. If you have one of those and you're operating it and you're successful with it, great, keep using it. You don't necessarily need to upgrade. But if you're looking to buy a new survey drone, we think it absolutely needs to be or ought to be RTK enabled. But the workflow does matter. How you connect the drone and its GPS signal to a local base station and then to a permanent base station for corrections and that sort of thing. With all of the different options for GPS workflows, there are more permutations than just on here. The simplest is no RTK, where you get all of your accuracy, all of your precision is coming from ground control points. Very simple field workflow, very easy to use. Other options are doing everything in post-processing kinematic on the drone. Pretty high accuracy. You don't need as many GCPs, but it's a pain in the butt. Using RTK, real-time kinematic, with some sort of local base station, that's actually going to be our favorite workflow overall. That gets you very, very high precision. You still need GCPs in our recommendation, which I cover a little bit. And then the last one, RTK over NTRP, which is the network protocol for streaming a lot of this GPS data. That works, but we don't love it. It's not going to be as accurate as actually having a local base station. The local base station really, really does make a difference in terms of overall accuracy. Another thing on the hardware side, as you are thinking about hardware, is LiDAR and photogrammetry. And this, I cover this in two places. One is when you're buying hardware, do you need LiDAR or photogrammetry? And the other is, assuming you have a LiDAR drone, should you actually use it on a job site? The questions you ask are going to be kind of be the same. Is what does the job site look like, and how much vegetation is there that you need to cover? This is where we were talking a lot. Again, thank you for those questions about the pulses of what LiDAR can do. LiDAR's main benefit, the reason why you would buy LiDAR, is if you do a lot of work in vegetated areas where you need ground cover, right? This is going to be the profile view of LiDAR with all of the, this real color point cloud on top is going to be photogrammetrically derived, and this false color one on the bottom is going to be LiDAR derived. You can see that the LiDAR pulses can actually see through gaps in this vegetation to make a very, very clean surface. You'll also notice, and it's worth saying, LiDAR is not perfect. It does no level of powerful laser will penetrate every type of vegetation. There are certain levels of scrub brush or oaks, or if you ever do work in more like tropical areas with broadleaf plants and that sort of thing, or in the south where there's like kudzu and stuff that's so dense, no level of LiDAR is capable of penetrating it perfectly. And this is kind of an example here where right here we see a gap where it clearly did not penetrate it. And that's where, when we're going to get to the post-processing side after the break today, we'll talk about how to address things like that. Partly because a human can look at something like this and say, well, it's pretty darn obvious that that slope is going to continue along here until, and then if you look at this in conjunction with the overhead ortho photo, it continues down here where the vegetation gets dense, and then this is actually a stream bed right here. So it kind of goes down until it becomes flat. That's easy for a human to see and for someone to determine, but very, very difficult for a lot of processing, automated processing algorithms right now. But anyway, the benefit of LiDAR is it gets you better ground cover, better penetration in vegetated areas. The benefit of photogrammetry is that it is faster, easier, more accurate on hardscape, and cheaper. And that is why photogrammetry still remains the most popular for just day-to-day surveys. LiDAR is the most popular for people that are experimenting with new technologies and how to integrate them in their business, but photogrammetry is far, far, far more popular still in terms of actually just getting survey work done. As far as just some like pictures to give you an idea of, if you do a lot of job sites that look like this, or even more, a lot of job sites that look like this, where you have some real dense vegetation and you need topo work, then yes, you will very much benefit from having a LiDAR drone. If this is what most of your job sites look like, then no, a LiDAR drone is not enough. This level of vegetation is really not going to make a difference with a LiDAR drone. A lot of people think it's like, oh, there are a lot of trees on that site, I need LiDAR. No, you really don't. Photogrammetry is perfectly capable of doing a complete survey on something like this without a LiDAR. Or of course, whether it's aggregates, earthworks, new construction subdivisions where there isn't a plant anywhere in sight, you definitely do not want LiDAR. At that point, it's just a pain in the butt and you're not getting any benefit from it whatsoever. The reasons to not use LiDAR, and again, this is what I was saying at the beginning about avoiding all of those pitfalls, why you should not use LiDAR. The hardware is expensive. They are bulky and hard to fly. And I really need to find a way to stress better how much of a pain in the butt bulkiness actually is to real world field operations. It's these little things that make the difference between a drone getting used a ton and a drone not getting used. The newest Mavic 3 Enterprise comes in like a lunchbox size case. It's incredibly easy to throw in the truck and carry it anywhere, whereas the M300 with any of these LiDAR systems that go on it, really any drone LiDAR system, is multiple cases, huge cases that often require two people just because they're so big and bulky to load into a truck, a briefcase full of batteries that might weigh 50 or 60 pounds just for the batteries. All of your additional sensors are in their own case. Just the LiDAR sensor on an M300 is about the same size as the entire drone surveying setup for a Mavic 3 Enterprise. that level of ease of use when it comes to these boring, repetitive workflows that I really like, that I want to see, I can't stress enough how important that is. And that's why we see so much more data from these photogrammetry drones than we do from LiDAR drones, is because really, honestly, a lot of the successful companies have learned you just bring the drone with you and you fly pretty much every site. Anytime you go, just fly it. A lot of people do it even when they're like, we don't need the drone data. It's probably faster to just do everything on the ground, but screw it. We'll fly it anyway. That way, if we miss something on the ground, we have the drone data. Or if the client says, hey, do you have any imagery of this? Or you think you screwed it up, we have the drone data and we can do it. People fly the drones with the Mavic 3s and the Phantom 4 series are so darn easy to use that people fly them without expecting to use the data because they're that damn easy to collect the data and they don't even process a lot of it. That's actually totally fine with me, right? That's the level of simplicity that you ought to get to in terms of field operations, is just kind of flying everything. All right, so moving on a little bit to talk specifically about the L1 sensor, DJI. This is DJI's LiDAR sensor. This is another one that there are a lot of questions about of, do you like the L1? Some surveyors do, some surveyors don't. Is it a powerful enough sensor? I don't know. Well, the L1 sensor, I'll jump to the conclusion first. We generally like it. But if your question is, does the L1 sensor have the most powerful LiDAR sensor? No, it does not. Is it going to get you the best accuracy of any LiDAR unit that is out there? No, it will not. The goal of the L1 sensor, in my opinion, is it gets you good enough LiDAR data at a extremely attractive price point for LiDAR. It actually says 40,000. They've recently reduced the prices on it. It's about 35,000 all in. That's not for the LiDAR sensor. That's for the LiDAR sensor, the drone, the batteries, the base station, the cases, the whole 9 yards, everything to actually get up and running with it, which is very, very affordable on the LiDAR side of things. Going to the data side of things, this is the part where a lot of people say, I don't know if I really like that. 2/10 of a foot vertical accuracy is what we can expect on the LiDAR. Sometimes we can get a little bit better than that, and that is admittedly with proper post-processing, which I'll talk about in the again after the break when we really get into the office workflow, the data processing, and that sort of thing. 2/10 of a foot vertical accuracy when you process it correctly, and people say, well, that's not really good enough. But then I'd almost challenge that assumption. Well, 2/10 vertical accuracy, look for topo underneath vegetation when you're usually only doing 1 foot contours on a site. 2/10 of a foot almost always is going to be good enough when you are talking at those, really ugly undergrowth areas. That's pretty darn good, especially when you are also getting photogrammetric data at the same time. The L1 sensor has a photogrammetry camera enabled, and with the right overlap, it captures both photogrammetry and LiDAR data simultaneously in the same flight. So you can actually get your hardscape features, your hard features, your paint striping, your curb lines, and things like that. You can extract from photogrammetry data, and your vegetated topo you get from the LiDAR data. With that blended workflow, we have found this to be absolutely good enough for the majority of surveys. And when we compare that to the more expensive LiDAR systems, right? If you take a microdrones LiDAR system or something like that, it's going to be 2 or 3 times more expensive, sometimes even more than that. And we've processed the data from it, and I can tell you for sure, yes, the data is better. The actual spread on the point cloud is going to be a little bit tighter because it has a much more high quality IMU, because the laser is going to be a little bit more properly calibrated and that sort of thing. But the end result survey is that it looks pretty darn similar. Maybe the topo in vegetated areas is slightly more accurate because of that LiDAR sensor. But it's not that this is incapable of it with the right workflow or that sort of thing. So we like the L1 because it's so much more easy to use and because it is good enough. But if you buy another drone because you don't think it is good enough, then I really can't knock you too much on that, as long as you actually are aware of what you're getting into with the more challenging workflow. But yeah, our favorite overall for land surveyors right now is this one, the Mavic 3 Enterprise RTK. It is small, it is cheap, it is easy. I don't care if you are a seasoned pro or if this is your first drone ever. This is our favorite overall drone right now. Photogrammetry remains the best workflow, cheapest workflow. Yeah, question? Yeah, you can. You can actually turn off the LiDAR scanner itself and fly it just as a photogrammetry sensor. I will say at that point, it is the photogrammetry sensor on the L1 is for all practical purposes the same as the photogrammetry sensor on a Mavic. So all of a sudden you're getting the same data as a Mavic 3 on a package that's about 10 times as big and 3 times as expensive. So whether that makes sense workflow wise, that's kind of up to you. But yeah, you actually can. If you want to know what our recommended workflow for that would be, is still fly it with the LiDAR sensor enabled, and then just don't use the LiDAR data. You can just kind of leave that on the memory card, save it. It's kind of one of those, like, it doesn't take any extra time to capture that data because the flight pattern would be the same, and you would just process using the imagery. That's a workflow that we actually do with a lot of LiDAR sites. People that only have the M300 or L1, they fly it with a LiDAR photogrammetry blended workflow or blended mission, gather all of the data, and we don't even touch the LiDAR data. We'll process the entire thing with the photogrammetry imagery. No, the Mavic 3 Enterprise RTK has a mechanical global shutter, which is part of why it is better than the Autel Evo 2 RTK, in our opinion. Yes, there is software that can correct for linear rolling shutter. It's not perfect. It really struggles on larger sites. It's a little bit more time consuming. It's just not quite as good, whereas this is a global mechanical shutter, which actually is part of why it is our favorite overall. It definitely had the, in the design process for this drone, they definitely had the mapping community. Mavic 3, all in around 10 grand. This is one where, again, it's often misleading, where it's like the drone itself you can buy for 4 or 5 grand or something, but then you need the extra batteries that are a couple $100 each, and then you need the RTK module, which is like $900 or so. You typically are going to need some sort of a base station with it as well, which, for a very long discussion on what base station to use, send me an email. We had a presentation on that yesterday, but long story short, $2,000 or something like that. So if you look in the $10,000 to $12,000 range, that's going to be the ballpark for everything you need to get this into a very high quality survey. Yes, it can connect to a lot of different networks. And again, I really recommend you looking at my talk that was all about that sort of stuff yesterday, because there are many different GNSS and post-processing workflows you can use, but they are not all created equal. We very, very, very strongly recommend having a local base station for the best accuracy on this, because baseline distances are much, much more important for drones than they are for ground-based surveying. They suffer from lower accuracy once you start getting to longer baseline distances for network corrections and that sort of thing. So yeah, this is our favorite. If you're getting started, or if you're adding a new drone to the fleet or replacing an old one, this one is absolutely going to be the best overall mapping experience, partly because it's just so damn simple to fly, and that's why we like it. Our favorite overall LiDAR system is this L1 for similar reasons. It's not quite as, I can't give as strong of an endorsement on this because, like I said, yeah, there is some noise to it. It is a little bit of a pain in the butt to use. But if you do enough job sites where there is vegetation and you need LiDAR, this would be our recommendation because it is just simpler and easier to process. All right, now we've talked about hardware. Let's talk about mission planning. This is what I've talked about before. The most boring, easiest to forget, but most important part to a mission. Mission planning is going to really be what sets you up for success throughout the entire process, through data processing, through field workflows. This is the most important part to get you to that boring, repeatable, integrated workflow that you can do time and time again. Unfortunately, for people that develop their own drone workflows just with the company, or especially when they have a drone guy, most common workflow that they have is send a guy out to the site, fly the drone to cover it with the site, give the data to a drone guy and see what he can get with it, and then hopefully that leads to some sort of profit. And surprisingly, this is not always the best workflow and doesn't always get you the data that you need. That is why we start with mission planning. It is not just a mysterious black box of go fly the drone and see what data you can get with it. It's just asking simple questions. Is this a good site to fly a drone at all? Are we surveying an airport runway where, yeah, you have to do a lot of paperwork, and regardless of the DJI unlock zones or anything, You're flying on an airport runway, you need to do the paperwork to make sure that the air traffic control tower knows that you're doing that. And I can say, we've actually done a lot of airport surveys as a company. We've probably done around 50 surveys on airport property with the proper communication with air traffic control and with the tower to make sure that the runway is cleared and they know there's a survey going on, and we get the drones unlocked so that you can do a survey of a runway in 30 minutes and get really good data. But asking yourself, is this a good site for a drone? Should I fly it with photogrammetry or LiDAR? Honestly, if everything that you've heard today, you have enough information to answer that question now. Should you fly a site with photogrammetry or LiDAR? What altitude should I fly at? Are you doing a 100-acre topo of raw dirt? Don't fly it at 100 feet altitude. You're going to want to fly it at 300 or 400 feet or something like that. What's the right overlap? We already have talked about that a good amount too, right? Photogrammetry only, 75-75. If you're flying LiDAR, our recommendation, 60 to 65%. And if you're doing really, really dense LiDAR cover or really, really dense vegetation with LiDAR, you might want to throw in a crosshatch in there as well. How many ground control points should I set? These are some of the things that once you're used to it, you have an RTK drone, probably set somewhere between 3 and 5, or if it's a really large site, 50 or 100 acres, then maybe set 8 to 10 ground control points. But if it's RTK, they don't need to be perfectly evenly distributed because you just kind of need to set them in the most easily accessible places. But simple questions to actually make sure that you're set up for success right at the beginning. Why do you care about mission planning? Well, number one is it does save field time, right? I'm actually, like I said, I'm pretty militant about spending less time in the field, collecting less data, and getting better results with less data. That's a huge thing for me. And mission planning actually is one of the best ways to do it. It'll let you set fewer GCPs, less ground surveying once you actually know what you can get with the drone. It can get shorter flight times, and most importantly, no field revisits. That is the most important part of mission planning. Make sure that you get your data right the first time. But it also does save office time. When you capture the right data, it gets processed faster. It is going to be more accurate. It can lead to fewer photogrammetry errors and a simpler drafting workflow when you're mission planning the right data, the right LiDAR or photogrammetry data. And in fact, if you're struggling with photogrammetry, the best thing that you can do is take a course on how to fly a drone, because the majority of photogrammetry problems, and actually now even LiDAR problems, the majority of problems with LiDAR data sets come from poor mission planning. So just asking questions, is this a good project for a drone? Well, start with size. Anywhere from half an acre, if it's less than half an acre, if it's just a very small single lot residential property, then maybe it's not the right site for a drone because it's easier to just shoot it on the ground. It takes time to fly the drone and process the data. Not a lot of time, but enough that less than half an acre, it doesn't make sense. North of 500 acres, you should really consider talking to one of the traditional aerialists where a manned airplane can cover a lot more ground in a much more efficient manner. Up to 20 miles linear for things like topo mapping, ALTA surveys, planimetrics, volume calculations, that sort of thing. Bad projects, like I said, are very, very large ones. Extremely high accuracy tolerances, a drone is not going to be the right tool. An example of that might be if you're doing a survey of a railroad and you actually need shots along the track. The tolerances that they require for the actual shots on the track are so tight, often just a few hundredths or something like that, that no drone, LiDAR, photogrammetry, or otherwise is currently capable of reliably getting you that data. You've got to break out a total station or some other type of tool to actually measure that. Indoor, underneath overhangs, sometimes people say, oh, can I fly a drone in a room like this? Well, technically, yes, you can fly a drone, but it's going to be the wrong tool for actually mapping something like this. You're going to want to blend some sort of ground-based LiDAR in with your data after the fact. As well as significant details under trees. That's another just interesting one with LiDAR, the way that it works. LiDAR is great for penetrating vegetation and getting topo underneath it, but it cannot see any details. For example, if there's a road that goes underneath full tree cover, the LiDAR will be able to get the topo of the road, but it won't be able to tell you where there's a manhole, because the manhole is going to be perfectly flush with the road, but it can't see the details under the trees. So oftentimes you might still need to get some details that are underneath trees that might be invisible to the LiDAR itself. Like I said, LiDAR, better cover in vegetation. If it's not vegetated, you probably don't want to use LiDAR with a drone just because not that you can't get good data out of LiDAR, but photogrammetry is just a faster, cheaper, easier workflow. Next up, I have a couple of slides here on safety and airspace restrictions as well. And this is what we were talking about, whether it's geofencing, that sort of thing. For anyone that is Part 107 certified, you've probably seen this chart. This is going to be your chart of the types of airspace that you have to study to get your Part 107 test, but then everyone forgets of what different airspace classes there are. Class B being huge airports, C is small airports, D is medium airports, and Class G, even though it's small here, what it actually comes down to in the real world, about 99% of the United States is in Class G uncontrolled airspace, a little more than 99%. But the challenge is that 1% of airspace that is controlled is often in the populated areas where there are more projects and where people want to fly. And for that, you have the LANCE system. This is the government's government system for gaining authorization to fly in controlled airspace. Yeah, like I said, most of it's within populated. You actually can, contrary to many popular beliefs, you can fly in any airspace in the United States. You actually can, with the proper approvals. The only question is how much time and paperwork you have. For example, if you wanted to fly a drone on the runway of SFO Airport, I can tell you that would take such an incredible level of paperwork and government interaction and all of that. It would be basically impossible, but technically possible if you were working with the right engineering company that was redoing the runway, they were shutting down the airport for a couple of days, and you got the approvals. You actually could, we just wouldn't recommend it. Smaller regional airports, those are actually a lot easier to shut down for just half an hour, work with air traffic control to get it flown, things like that. But the majority of airspace, even controlled airspace, you can work with LANCE, which is this automated online system. You just use an app on your phone, say, I want to fly here, and that sort of thing. And that gets you what's called an airspace authorization, which is just a real temporary one. If you are interested in the legal side of things, there's another regime called waivers that you can get. LANCE airspace authorizations are the easiest ones because you can get them online, you can get them instantaneously. Manual airspace authorizations, those are what you typically need when the online map says that like your automated LANCE approval is at 0 feet above ground. And that means, well, you can't get automated approval, you need to go to the manual approval. Manual authorization is typically the route that you want to go there. And then there is another process called waivers that we would generally not recommend. This is government paperwork we're talking about here. So you're trying to do the same thing, but it's two completely different teams, two different routes to actually get it. Waivers are a very long process, a couple months long to actually get an airspace waiver, but that's going to be if you're flying in controlled airspace multiple times over the course of a longer period of time, then maybe the waiver is the right way to go. But for the majority of projects, you're going to want to go through either the automated authorizations or manual airspace authorization. Another question with safety is actually just about flying drones in the real world. People say, oh, there are these rules about flying at night and flying over people and whether this drone is authorized to fly over people. And the real answer to that is that when flying drones in the real world, just use good judgment. There are, if I could sum up the laws, and don't get me wrong, I've read all of Part 107 and all the adjustments and all of the proposals and all the new things. And I've also had the benefit of speaking to a lot of people that work at the FAA, both on and off the record and that sort of thing. The FAA, their main goal, their primary goal is don't screw with manned aircraft traffic. Beyond that, they don't care at all. They don't care if you crash your drone. They know lots of hobbyists crash their drones all the time. They're fine with that. They actually don't care who you fly over at all as long as you stay the heck away from manned aircraft. That's their number one goal. So when it comes to flying over people, that's one that they're like, yeah, they actually kind of don't care. They technically don't want you to hurt anyone, but most drones, it's an interesting little statistic. The number of deaths caused by small drones, well, I suppose outside of Ukraine nowadays, but in the United States, the number of deaths caused by drones is 0. There are hundreds of millions of drones and millions of drone flights every single day in the United States. Even just minor injuries are extraordinarily rare with these things, and it has never caused a single fatality. which is honestly a great testament to the safety of these drones. The drones that I talk about now, these DJI drones at least, their level of reliability is staggering how good they actually are for modern day drones. 5, 6 years ago, drone crashes were a lot more common, but they just aren't now with new drones. Now, I can't say the same for a lot of the more bespoke, low volume manufacturing, less common drones. They don't have as many hundreds of millions of flight hours as a lot of these DJI drones do. So they do see errors, software errors that lead to motor shutdowns, that lead to crashes and that sort of thing. I'm not trying to scare you or anything, but I just want to be honest that those are a little bit more common in the higher end drones. You would wish it were the other way around, but actually, the Mavic series is probably going to be the single most reliable drone in terms of actual flight data. But to go over that, I mean, once again, flying drones in the real world, the FAA is looking for bad actors. They're not looking for minor infringements. They're not trying to get you a ticket because you flew over a highway. I can tell you, people flying drones over highways is extraordinarily common as long as you're just responsible. If you're flying a 300-foot survey over a highway in a back and forth flight pattern, you're not going to get in trouble. If you take your drone and try and dodge between trucks on a highway where they can see it and you're putting it on YouTube, then yeah, you're probably going to get in trouble for something like that. So just use your good judgment. No one, the FAA doesn't have police. You're not going to get in trouble for anything. And then the last thing I just want to cover quickly before we get into the break is the autopilot software that you use on your drone. And really, most autopilots, like a lot of things in drones, 4 or 5 years ago, this was a huge topic of debate. People would buy special drones and special controllers because they wanted to use the right autopilot software. But we've seen an awful lot of convergence in the different autopilot softwares out there in terms of how they work and the features that they offer, partly because mapping software has, like I said, we've realized what works and what doesn't. So we don't have a strong recommendation. If you have a software you like, great, use it. In fact, our only recommendation would actually be, especially with most of the modern drones, they actually come with autopilots installed in the system, first-party autopilots. The DJI drones will have a DJI autopilot. The Autel drones will have an Autel branded or that sort of thing, autopilot built into the controller. Those actually have become our favorite. Even though sometimes the third-party autopilots might have a little bit of a smoother user interface, a little bit easier maybe to import a digital terrain model for terrain-aware mapping, things like that. But generally speaking, they're pretty similar. Use the one that's on the drone would be our recommendation. One of the only things to talk about with that is, with autopilot software, is this idea of terrain awareness. So terrain awareness, for those of you that aren't familiar, is drones like to fly to 150 to 400 feet above ground. But there are some sites, particularly larger or more mountainous sites, where you actually have significant terrain changes. Terrain awareness uses a base map, a base terrain map that's usually from the government, like a global or national scale map. Specifically, it's almost always SRTM if you're interested in that side of thing. As a base layer so that the drone tries to stay approximately the same altitude above ground throughout the entire project site. This is really, really useful on projects that are larger, more than 50 acres, that maybe have more than 100 or 200 feet of relief. And what this does is it ensures that you have the right level of overlap at every part of the project. And that overlap matters for both LiDAR and photogrammetry. You want the overlap to be the same so that everything processes, that you get reliable data, you get it accurate. It's only available on some autopilots. It's definitely on the DJI one. It's a little bit clunky to use though. So it's one of those things where we don't recommend using terrain awareness on every single flight just because it's a little bit clunky to use. You do have to import the right terrain model and you have to make sure that your flight above the terrain model is at the right level. It's totally doable. Just follow a checklist, a tutorial, something like that. But it is a little bit more difficult to use, but absolutely can get you much better data on flights with a lot of terrain. And with that, I am seeing it is currently 10 o'clock, which means that you have heard me talk enough. One question first before you get coffee. A lot of things. Anything from rolling hills where you have 100-foot hills to cliffs where you're working on a coastal cliff where you might have 100-foot cliff between or a bluff of some form. Likewise, even if you have a project that's just a slow grade up the side of a mountain and it starts, or up the side of a road that's just going uphill and you're doing a mile long road, and a mile that way is 200 feet higher than where you are right now, you should have a drone that slightly follows that terrain up and then slightly follows it down on the way back. There are all kinds of different things, like a quarries, right? Actually, quarries are a little bit trickier, I should point out, because the base terrain that you use for terrain awareness might be old, and quarries change their terrain by very significant amounts very frequently. So if you actually are doing any sort of terrain aware flight on an active quarry, you've got to be extra careful about what your base, the base surface model that's used in terrain awareness is. All right, so with that, we will now take a 30-minute break, and I'll let you guys get coffee, and I will see everyone again back here at 10:30. All right, so we can get things started. Last session of the day. Thank you all for staying to the end. I know they have the grand prize drawing coming up, which apparently is right here. I was just checking it out, that there are apparently couple bottles of wine, a VR headset, and a basket of all kinds of other stuff. So I'm not sure if there's a moderator that was supposed to be here or anyone else that may have left because of the impending storm, which I know is always on people's minds right now, and mine as well, as I was just checking my flight stats to see if I'll be making it. So far, so good. But yeah, we can dive right into things and wrap things up for the last bit on mission planning, and then we're going to cover most of what I'm going to talk about in the second bit is going to be with regards to the data processing aspect and the data processing workflows. So with the last part of mission planning is going to be about flight altitude, overlap, and accuracy. We've already talked a fair amount about that with all of the questions, which again, thank you for the questions. I always appreciate those and want to keep them going. But one of the things that we haven't talked about is something like flight altitude yet, that we haven't really talked about in detail, but it's very, very relevant in terms of the accuracy of the project and the total amount of data that you actually get. The way that I always, the first thing that you want to start with when thinking about flight accuracy or flight altitude and accuracy is really starting with your desired results. Because we have a lot of people that say certain things that they want about a project that lead to some unexpected consequences. For example, we hear a lot of people saying things like, I want the absolute best possible accuracy that I can get out of it. This applies to both buying a drone and flying a drone. I want the best possible accuracy. Or maybe they say, oh, just fly it as low as possible so that you don't miss anything, that we get the best resolution we can. Fly it super low. Or maybe we'll fly it first and then we'll see what data we can get out of it, and we'll figure it out later. These by themselves don't sound like crazy statements. They're not crazy statements at all, but they do lead to some unexpected kind of consequences. For example, saying you want the best possible accuracy, what that ultimately leads to is really expensive data collection and processing costs, because you're going to be collecting so much data with really expensive equipment and really complicated workflows that it winds up making your processing side really, really tricky. Same thing, just fly as low as you can so that we don't miss anything means that the project is going to take weeks or months to complete, because what could have been done in 20 minutes in the field might take 4 hours. And what could have been done by gathering 200 or 300 photos on a project site now is 2,000 or 3,000 photos, and it takes much, much longer just to move the data, to process the data and manage it all together. And fly it first and we'll see what data we can get. Well, oftentimes that means that the data is useless. If you don't know what you're trying to get from it, then you'll never get it. So it's always an interesting thing to see these not crazy questions that lead to some real unexpected results. So by starting with your desired results, knowing what accuracy you actually need, that can influence what your flight altitude ought to be. This is a real rough table that's that actually has held up pretty well over time with all of the different drone technologies, of about what accuracy you can get and about how much area you can cover with a drone. And what you'll see is if you want 1/10 of a foot accuracy, that's usually the target for a lot of things, particularly on hardscape, is around 1/10 of a foot accuracy or better. Well, in a single flight, you can cover about 10, sometimes a little more, 10 to 20 or so acres. If you're flying at 150 feet to get there, but that would capture on the order of 6,000 photos per 100 acres. For anyone that's touched photogrammetry processing, 6,000 photos is a heck of a lot of data and is a big pain in the butt to process. Likewise, if you were to fly the same exact, call it 100-acre site at 400 feet, you would capture about 750 photos, almost a factor of 10 less. And your accuracy would go from 1/10 to 2/10 of a foot. And this is where that kind of danger can come in of, I want the best possible accuracy. That means you're trying to fly every site at 150 feet. You have so many photos that you kind of kill yourself on that sort of thing. The processing just ruins everything. Whereas if you were just doing 1-foot contours, if you were doing, and this is something we see a lot, right? Especially for 100-acre sites, you're not getting ultra sharp detail over the entire project site. Typically, what you want is topo, and you need 1-foot contours, or maybe even 1/2-foot contours, or something like that. And what you'll see is the 400-foot flight altitude is perfectly, except 2/10 of a foot accuracy on a single shot is more than enough to get you 1-foot or even 1/2-foot contours. In the real world, what we actually see is most drone flights fall into the kind of 200 to 300 foot range. That's really the Goldilocks zone for the majority of projects. That's good enough accuracy for most projects without burying yourself in data, without anything like that. So starting with your desired result, knowing and being honest with yourself about what accuracy you actually need is pretty important. The next thing that I want to talk about is flight patterns. This is a little interesting because there are multiple types of flight patterns out there, and we generally, for most applications, recommend this, a single grid flight pattern, or what is known as a Boustrophedonic flight pattern, also known often as lawnmower style, where it just goes up, down, back, forth, back, forth, back, forth. There's some drone autopilot apps out there that call these a 2D mission maps. In fact, that's one of the screenshots here, is it says, grid for 2D maps, which is really, really misleading. This sort of Boustrophedonic flight pattern is absolutely, completely acceptable for 3 dimensions, and the data very, very much proves it out. Because the alternative, what a lot of apps push is a double grid flight pattern, where one grid goes north to south, the other rotated 90 degrees east to west. This captures about twice as much data, depending on if you aren't changing any other overlap settings, twice as much data, which winds up making your processing time take about 4 times as long, because processing time is nonlinear. And for the overwhelming majority of missions, it provides no statistically measurable benefit. Now, there are a couple of outliers there, like I was saying, with LiDAR projects, for having different angles, this actually can improve some vegetation penetration. But for the overwhelming majority of photogrammetry missions, single grid is going to be half as much data, half as much time, and exactly the same level of accuracy. We've done lots of tests proving that out. That said, some people still insist on capturing double grid data. They think it's more accurate, it's more reliable. And if you want to take that extra time processing, then be my guest. But I'm just kind of here to let people know that the data does not prove out that this actually gets better data for photogrammetric mapping. A couple of caveats on that. If you are actually doing 3D modeling for, say, making a map of a video game, where you need the facades of buildings to be much crisper and have better resolution on the facades of buildings, then yes, a double grid flight pattern for photogrammetry will get you better imagery data on the facades of buildings where you have windows and doors and things like that. For surveying applications, however, you usually don't care about how pretty the windows on the side of a building look in a 3D model. What you care about is how the height of the building, the footprint, the topo, the paint striping, things like that. And for those circumstances, there is no benefit for the double grid, or like I said, very, very negligible benefit. So those are just the 2 most common flight patterns. There are also a few other ones, like linear missions. Linear mission planning is great, where the drone flies back and forth a few times over the course, over a road. A couple of things on the data side from there. Number 1 is we would recommend a minimum of 3 parallel flight lines, not 1 or 2. Yes, you can mathematically and based on the rules of physics get away with 1 or 2 flight lines. From a workflow reliability standpoint, we strongly recommend a minimum of 3 flight lines on any linear mission plan in order to get enough overlap to properly calibrate the camera, account for any sort of other just errors or a missed photo or something like that. free flight plans is definitely what we would recommend there. And then the last type is terrain awareness, which we already talked, where you import a DSM. This is just an example of, kind of crazy linear mission plan that goes back and forth. And this is what the terrain surface based on that underlying elevation model would look like. Terrain awareness works great for both linear mission plans as well as for larger sites where you do have more than 50 or 100 feet of elevation change over a project site. But when it comes to mission planning and actually picking your altitude, the most important thing to note is that in the real world, there absolutely is such a thing as too much data. I don't love the type of people that say, oh, more data is always better because you can filter it out. Yes, you can filter out certain data. You can process with less data. You can use more computer processing time. But that's a telltale sign to me that someone's looking at this from a research project standpoint. They're not trying to turn it into that boring, repeatable business workflow. To get that boring workflow, you don't want too much data. You want only the data that you need, because anything else just takes up time and money and processing costs and labor costs and all of that stuff. And the recommendations to me to make this that boring, repeatable, profitable, useful workflow is, well, don't fly lower than you need. If you are doing 1-foot contours on undeveloped land, you really should be flying at 400 feet, basically all the time. If you are doing a as-built survey of a gas station or something, then yeah, totally fly at 100 feet or 150 feet, fly lower, get all of those details. You won't drown yourself in that level of detail on a site that's only a couple of acres. But if you are doing just straight topo, fly higher. That's actually a good thing. Another thing that I haven't actually mentioned here is from flying too low, a lot of drones can often suffer from what I like to call like the drinking straw effect, or trying to survey through a drinking straw. When you get so close to the ground with these drones, anything lower than 100 feet, the actual footprint that the drone can see on the ground is so small that it makes it much more challenging to do any sort of 3D mapping on it, because it's only seeing a tiny footprint of the actual ground. And to cover a couple acres, you have to use so many photos, you have to interpolate across so many different images that you actually wind up getting worse accuracy if you ever go lower than about 150 or 100 feet. So that's part of why 150 feet is kind of our practical floor, the lowest that we would ever recommend. And then, like I mentioned before, don't use LiDAR if you don't need it. LiDAR is going to be a great way to spend a lot of time processing data that you may or may not need. If you need LiDAR, use LiDAR. But if you don't need LiDAR, don't process it. You can still collect that LiDAR data and not process it. That's totally acceptable as well. Talking a little bit more about overlap, this is another one that we talked in a good amount earlier. Photogrammetry overlap, general recommendations, 75-75. And our recommendations for LiDAR are going to be about 60 to 65% swap to swap. Part of the reason that we actually like 60 to 65% swap to swap for many LiDAR sensors, or for many drones that have both photogrammetry and LiDAR sensors simultaneously, it turns out that these two overlaps are pretty darn close to one another because of how the field of view of the camera works. If you have a 24mm lens, which something like the Phantom 4 or the L1 or the Mavic 3 have, effective focal length of 24mm, they flying at this fixed altitude. If you fly a 75-75 photogrammetry mission, your LiDAR will end up having about that 60% overlap based on how the field of view of the LiDAR and the camera kind of are different. So that actually works out really, really well to allow you to fly LiDAR and photogrammetry simultaneously on the same mission. The next thing when it comes to flying photogrammetry, at least, is flying nadir versus oblique imagery. And this is another one where there's actually an awful lot of misconceptions here, partly, I think, driven by some of the softwares that really push more oblique imagery than I think is necessary for survey. So nadir is when you are looking straight down. This is the camera, and it looks straight down. And the way that a camera works is it actually takes a picture. It's not just straight down. It actually takes a picture in a cone. That's part of what the field of view is. The field of view of a camera for most of these drone mapping cameras is actually going to be 84 degrees, or if it makes easier sense in your mind, just about 90 degrees, like a right angle approximately. And what that actually means, if you kind of look at this, even when the camera is pointing absolutely dead straight down, the edges of that photo are actually hitting the ground at a 45-degree angle. It's at an angle. You can see the facade of the building. That's not just a problem, but that is fundamentally exactly how photogrammetry works. You are taking photos of the ground from different angles. And so people say, oh, I need oblique so that I can see it from the angles. But for most purposes, a 45-degree angle, or approximately, it's a little bit less than that in the real world, is going to be good enough that you don't actually need any sort of low oblique or high oblique imagery. And there's another hidden side of this, that if you take it at high oblique, you actually are lowering the resolution of your final product, what's called the ground sampling distance. This image does a really great job of showing it, when, or at least at the extreme levels. If you look at the size of these squares, when the drone is kind of the part that's closer to the drone, the squares are pretty big. And out towards the horizon, the squares get smaller and smaller and smaller and smaller. You actually can see less detail. So by tilting your camera up, by flying at obliques, people say, oh, I can see it from angles. That'll help me maybe see under trees a little bit better. That'll help me get my vertical accuracy a little bit better. The actual data and statistics doesn't really bear that out in most circumstances, at least not with the drones that do have, over 80-degree field of view or something like that. What you actually are doing, you wind up getting less resolution. So more overall data with more photos and lower final resolution because it's further away from the drone. This is going to be another one that's kind of close to that. You can see how big the squares are here, and just further away, they're just a little bit small. And that actually does, on a statistical measure from a whole project site, it does make an overall impact. So for us, we do generally recommend nadir imagery. We have not found any meaningful impact for surveyors from any sort of oblique, adding in oblique imagery. Again, there are going to be edge cases where that is not the case. If you are doing the modeling on the facades of buildings, if you have a near completely sheer cliff wall and you need to get the facade of the cliff wall or the face of the cliff wall, then yes, adding in oblique imagery can actually help with that. We are trying to get details on the vertical features themselves. Oblique imagery can help. But that is the exception, not the rule in survey. In survey, most things, nadir is going to be better. And oblique imagery also is going to, like I said, lower resolution, but it's going to increase your processing time. And the resulting accuracy is rarely improved by adding obliques. This is, again, one where we've actually done a number of studies, a number of white papers, take the exact same site, fly it once with just single flight pattern overlap, 75-75 overlap, and then fly it again with double grid pattern, and then again with oblique imagery and multiple things. And what you see is there is no statistically significant difference at all in the accuracy of flying these sorts of obliques or overlaps on the majority of missions. It is not, statistically, it is completely insignificant. Like it does not change it. So just kind of a summary of some of those mission planning best practices. Single lawnmower flight path is our recommendation for most projects. 75-75 overlap for photogrammetry, or 60-65% for LiDAR, and nadir only with no obliques. Last thing I'm going to talk about is planning ground control points. And the first thing to talk about when planning ground control points of where to set them and how many to set them, the real factor that makes a huge difference in mission planning is what type of RTK or PPK GNSS correction system you are using. Whether you're using a local base station, which we talked about earlier, that is very much our recommended solution. Whether you're using a network correction service or no ground control points at all. Generally speaking, if you use no RTK or PPK, rule of thumb, you need 5 control points for every flight battery you use. They need to be pretty well evenly distributed, set around the corners, around the center of the site, something like that. Whereas if you have RTK or PPK, really any of these ones at all, you need a lot fewer ground control points, and they are much less sensitive to their position. For example, with a site, if you can only access one side of the site because that's where the road is and the rest is very steep and off the cliffs, it's nice to have them on higher points and lower points to help with calibration, but it's not strictly speaking necessary because a lot of the precision within that drone flight is going to be coming from the actual onboard RTK nowadays. we were talking before the break a little bit about these network solutions. So actually connecting to a network RTK or a virtual reference station or anything like that. We generally don't recommend using network RTK or permanent base stations only because the baseline distance is too long for a drone. Drones are not like ground-based surveying GPS where you can set up your survey pole and you can take a 5-second observation and it averages out over 5 seconds because the drone is moving 30 feet per second sometimes, and every observation is at a new place. If you lose that RTK, that fixed solution for even a split second, it can cause a lot of problems and it just lowers the overall accuracy. These sorts of network solutions and network-based corrections are really great for ground survey. They're actually really good for GIS accuracy as well. If you're doing GIS level projects where you only need about a foot of accuracy, network corrections might be great. But typically for survey where we are looking to target that kind of 1/10 of a foot accuracy, you really want to have a local base station, some sort of local correction. As far as ground control points, like I said, minimum of 3 ground control points is our recommendation per project as a minimum, or 5 if you don't have RTK, plus a good rule of thumb, an additional ground control point for every additional flight battery you use, and don't rely purely on the RTK or PPK of the drone. And with that, I'm saying, the question is, well, do I still need ground control if I have RTK or PPK? And the answer is that good RTK or PPK, technically, no, you do not. It is technically possible to process an entire project, survey grade accuracy without any control at all. However, in the real world, we have no control is just not going to be good enough. That's because you really need your ground control to properly calibrate the camera. If you've ever done this with either a DJI drone or honestly any non-calibrated camera drone, what you can see is even if the RTK data is perfectly or not RTK data, the GPS data and GNSS data is perfectly post-processed, you can process it in a photogrammetric engine multiple times, and you will see quite a bit of vertical differences from one processing round to the next. And that's because of how these softwares and how these low quality uncalibrated cameras are calibrated. The way, like, these slight changes in the effective focal length can actually move your entire surface up or down by a foot, even if your actual drone, the RTK geolocation of the images is in exactly the same place. So that's part of why, especially with these types of cameras, you really need control to get that 1/10 of a foot accuracy. Otherwise, you are going to see some variance. And localizing your project and detecting errors, because like I said, human error, honestly, so much of this is about workflows, right? It's not even about the most high-end, cutting-edge checklist software or using that sort of thing. Because realistically, that's not where surveyors make mistakes. Surveyors, all of you guys are pretty smart people, and you can figure out the mathematical side of that is a lot weirdly easier to figure out. The workflow side of how to prevent human errors, how to catch human errors, and make it reliable, that's the hardest part of this whole business. As far as marking ground control, there are a couple of different, options that we don't love. Some people use just like entirely single color panels or ones that are really reflective that wash out in the sunlight. Those can cause a little bit of error. We also really don't like things like corner of concrete because for a photogrammetrist, these are often very difficult to identify, especially if the notes just say corner of concrete and you say, well, is it that corner? Is it that corner? Same thing with like end of parking stripe, that sort of thing. A lot of surveyors use chevrons too. As a photogrammetrist, I do not like chevrons personally, partly because there seems to be a very different interpretation of how to mark them. A lot of surveyors mark them on the tip in here. Some surveyors mark them on the inner corner. Some surveyors actually mark it in the middle point, like right there in the white part. And every surveyor thinks the way that they do it is how everyone else ought to be doing it as well, but they don't realize that everyone does it differently. So I don't like chevrons for that reason, because we don't know who marks it how. And we also see some really creative ways of marking ground targets as well. So if you want to do that, actually, good on you. You can keep marking a target that way. Those are funny. But generally, a checkerboard style one is really good. We actually sell a lot of these just like paper, cardstock, biodegradable ones that are pink and green. An interesting just kind of legacy from the old world of photogrammetry mapping photogrammetry mapping with highly calibrated cameras used to be done entirely in black and white. And so the best way to have a target was either a pure white cross or a black and white checkerboard pattern because it showed that high contrast that was easy to see from a black and white imagery. We don't live in a black and white world anymore. No one uses black and white cameras. So, but ground targets are still often black and white. And our photogrammetrists learned, yeah, we really love these obnoxious colors that if you stare at them long enough, it makes your eyes hurt. But the benefit is you can see these things from space practically. They're very, very visible. So we like high colors. It doesn't have to be, there's no accuracy benefit from using ridiculous watermelon style colors for a ground control point. They're just as accurate as black or white, but we found the little things. In fact, the reason that we started manufacturing these targets was out of requests from our photogrammetry team. Our photogrammetry team said, hey, like these targets are often hard to find. There's so much just like debris or junk or other white paint on a road that finding the right black and white target just takes a while. Can we make colorful targets? And we said, yeah, we can. All right, so that's it for the actual mission planning and targets. Now let's get into the office workflow of what it looks like to actually process this data. The office processing workflow, this is kind of the latter half of the processing part. And the reason I spent so much time on the mission planning is, quite frankly, if you get the mission planning stuff down, if you nail the mission planning, your office workflow is going to be a heck of a lot easier. Like I said before, the majority of errors in processing, the majority of struggles that people have in processing actually come from mission planning, not from not having the right workflow or the right software or the right computer or anything like that. But it still matters, and that's what we're going to cover right now. So the first step, like I said, is point cloud processing, which is going to be both photogrammetry and LiDAR. So photogrammetry processing is when you take all of those photos, stitch them together, create a point cloud, an ortho photo, and typically a digital surface model. Digital surface model being the surface, absolutely everything you can see, including things like trees, buildings, et cetera, et cetera. It is when we get to things like digital terrain models that is when we filter all of that out. LiDAR processing, also part of that point cloud processing step, that 3D modeling step. It's when you classify everything, or you create your LAS point cloud, you geo-reference it, creating a digital elevation model out of it, and converting a point cloud into useful formats. We don't consider point clouds to be a final deliverable. Many people do. But our personal belief is that the point cloud is only an intermediate step of actually getting to a surface, that typically a surface or a CAD file is what your actual final deliverable ought to be. And then once you actually have those rich models, you go through line work drafting to reduce it into a CAD-friendly surface to actually get your proper layers, your points, your polylines, that sort of thing. And then you finish it in CAD where you merge in your field shots, you merge in things like boundary. You know, that's something that I never talk about much is boundary because, quite frankly, drones don't do boundary. You can't do boundary. That is both legally very protected, but also something that drones can't see legal lines at all. But finishing it in CAD matters because oftentimes you are doing a lot of the topo from the air, and then you do the boundary on the ground. You have to merge it all together. That all goes together. So just to kind of summarize what a lot of this looks like all together. So you start with photos, ground control, RTK, PPK data. This is kind of the raw outputs from your data collection stage. It goes through this photogrammetry and LiDAR processing step, which will create a couple of different deliverables, usually a point cloud, a digital surface model, and an ortho photo. Then it goes through what we call the line work drafting stage. That's where you have your drafters actually vectorizing and extracting this data in a 3D points, polylines, typically going to be in a DXF format. Then it goes into the final CAD stage, CAD finishing, final quality assurance, which is where you merge everything together, create your surface, contours, site culture, usually in an AutoCAD style DWG format, depending on what software you use. And that's what gets you your final deliverable. This workflow is pretty important. And the other thing that we've found is really important with this is actually making it each step fairly discrete, that you don't get to go into line work drafting until you are done with photogrammetry processing. A lot of people run it through photogrammetry and start doing line work drafting, and then they'll find an error and they'll have to go back and do more photogrammetry. And that's a real quick way to just spend a whole lot of time. These steps, we like having them pretty discrete. Yeah. Great question. I'll cover that in just a second. The answer is a lot of different ones. But using things like Global Mapper or Virtual Surveyor, we use QGIS for some of this stuff as well. Oh my gosh, I'm drawing a blank. What is the Terrascan is going to be one of the ones that we use heavily for LiDAR as well. Mm-hmm. Great question. Let's talk about photogrammetry. So yeah, getting a little bit more detail into photogrammetry. Photogrammetry, starting just from the high level, and we'll get into that, is the art and science of making measurements from photographs. You start with 2D photographs and you turn them into a 3D model. This photogrammetry is not at all proprietary to the drone. You can do the science of photogrammetry, and in fact, most photogrammetry software can work with absolutely any image taken from any source. You can use old school photo negatives that have been scanned into a digital format and run that through modern photogrammetry software. You can import the camera setters, the actual geolocation data from an Excel file and tie it into the photos that way. Or you can have it use no geolocation data whatsoever and use just the ground control points to force geolocation on the entire project. The softwares itself are very, very, very flexible on that sort of thing. They are not proprietary to the drones. There are definitely some market leaders out there. Pix4D is by far the most common and they are the market leader for survey grade mapping quality, that sort of thing. There are some other softwares out there, things like Drone Deploy as well, which is very, very good. They're a cloud-based solution, but typically not going to be quite survey grade accuracy. They don't offer as much manual control over a lot of the photogrammetric process, but they are very, very fast and affordable because of their nature as a automated cloud service. But the biggest challenge with photogrammetry is actually not even the knowledge skill, it's that it takes a lot of time. It takes a little bit of human time and an awful lot of computer processing time as well. This is, again, the nature of modern digital photogrammetry. You're not working on a stereo plotter, but you are working with 2,000 photos that altogether might find a few million individual automatic tie points for matching, and then try and create a few 100 million points in a densified point cloud. And that takes a lot of time. So experimenting with photogrammetry, part of what makes it a really long learning curve is that many projects, when you hit process, you basically don't get to see anything until the next day, and you review the results and hope they're good. And if they're not, it takes another day to run another test and figure it out. And improved hardware only does so much. This is where, again, people often overspend on gear because they say this takes a long time. I should buy more computers and that sort of thing. And so they'll take, a $4,000 computer, and then instead they'll buy a $10,000 computer, and they'll see their processing speeds improve by 20%. And so all of a sudden, instead of taking 8 hours to process, it takes 6. But that kind of isn't a big improvement because it still usually means you're clicking start and you're waiting overnight. So you just spent $10,000. And in the real world, you didn't actually improve your processing speed because it's still processed overnight before your person comes in to process it. That's why, improving, like buying more expensive computers usually isn't the answer. Whereas if you have a better workflow for how to process this sort of data, you can cut that from 8 hours of processing maybe into 2 because you took a lot fewer photos in the field and it processed quicker. So that's why a good workflow is better than a good computer. When it comes to photogrammetry workflows, we very, very much rely on an iterative loop. So when we talk about an iterative loop process, we start by processing everything in ultra low resolution. So we import the photos into a photogrammetry engine. We are powered by Pix4D. That's our primary photogrammetry engine, although admittedly we are familiar with all of the other ones as well that we use, whether it's Agisoft Metashape or some of the open source ones like OpenDroneMap and things like that. But yeah, we run it in very low resolution first to save time, check for any blunders, make sure the overlap's there, make sure the images is good enough, get the basic rough geolocation down, marking the first control points, marking all of the rest of the control points, re-optimizing a process still in very low resolution, repeating until we get that low resolution version completely processed. And then we start scaling it up to full resolution processing.
getting all of the error triangulation done properly, making sure the GPS residuals are good, making sure the confidence of the geolocation data is in line with how accurate we thought the images were. A lot of these statistics that these photogrammetry programs provide, or at least the good photogrammetry programs provide, include things like the geolocation variance, right? If your photo center you said was here, and on average there is 0.3 of a foot of variance between the computed geolocation of the photo and the initial estimated geolocation of the photo. 0.3 of a foot, is that good or not? Well, it depends on what you were expecting. If you had a non-RTK drone, 0.3 of a foot is crazy good for the geolocation. If you did have RTK, I might see 0.3 of a foot and say, ooh, we might have some geolocation problems here. There's an issue if our geolocation variance on the processing side is not where we want it to be. And that's one where you want to discover that as early as possible, before you create an orthophoto, before you create a full resolution densified point cloud, before you create a 3D model. You want to be able to have stops in that process so that you can see what the errors are and then start checking more data. What's going on? Is it coming from the ground control points? Is it coming from that? I've given other talks in the past that are much more detailed on the actual photogrammetry troubleshooting process. But photogrammetry is definitely a long learning curve science with a long tail of things that you can learn. But yeah, managing processing time is really the most important thing when it comes to photogrammetry. And most of this is decided in the field with mission planning, right? I was hammering earlier on saying there is such a thing as too much data, overlap overkill, too high overlap. We've seen people say, 75-75 overlap is good, then 85-85 is going to be better. That is not the case. It's just more data, and it's a pain in the butt. Partly because with these photogrammetry engines, processing time is very nonlinear. If you double the amount of photos, you typically quadruple the processing time, which is just a nature of the architecture of the software and how they do all of their various bundle block adjustments and that sort of thing. But yeah, processing time is completely nonlinear. And the solutions are a good workflow is much, much more important than a good computer. That makes someone like me sad because I like good computers and I like having my really powerful latest generation CPUs and graphics cards. But having that iterative workflow, staging your processing, running an initial process multiple times, starting with very low resolution, running it really, really rapidly, like in an ugly way that wouldn't be considered survey, just to start the process and then scaling up from there. That's how you save time, not buying a new computer. That said, everyone says, well, what computers do you guys use to process? And here's some of the information of the current generation of processing computers that our photogrammetry team actually uses. And for people that are super familiar with computers, you'll look at this and say, oh, that's a good, but not like insane level processing rate, right? This is not going to be enterprise server grade computers or anything. This would be a high-end gaming PC, right? It costs a couple $1,000s, but not tens of thousands of dollars or anything like that. And we found that with a good workflow, not only are these more than enough, these are actually ideally what you want for a lot of these processing things. And when we need more processing power, we typically will buy an additional computer, and a single photogrammetrist might be working with 4, 6, or 8 computers of a architecture similar to this, rather than one $20,000, server grade computer or anything like that. We found that to be just a little bit more efficient, but some of that's based on your own software architecture as well and how you do that. As far as ways to process it, which softwares you use and how you do it, there are 3 main categories of ways that you can actually process photogrammetry data. The first is automated cloud-based processing. This is typically by companies like DroneDeploy or Propeller, or Pix4D actually has a cloud version of theirs that's a little bit more advanced. If you are going to use a cloud service, Pix4D's cloud is going to be probably the best one out there. They are typically going to be much more affordable than the other options because you don't need to buy your own hardware. You're effectively renting theirs. They're typically going to be pretty fast and pretty scalable. You can deal with an awful lot of data through that. But the downsides, they're not quite as much accuracy. You typically don't have quite the level of control that you would otherwise, and not as much support or anything like that. Again, Pix4D is actually doing really good stuff with their cloud-based processing that will give you a lot more control, but then of course it costs more that you might actually wind up spending a lot on cloud-based processing if you process a lot of data in an iterative manner, because you're not just buying the software, then you're paying for every project. The other option are local software processing. This is going to be Pix4D and Agisoft Metashape or Bentley Context Capture are going to be some of your more popular ones out there. Highly customizable, most control, but the downside, it's expensive, both from buying the software, which is usually a couple $1,000s per year for a license, and from buying the computers, a couple $1,000s per computer, something like that. But the really biggest challenge there is the long learning curve and that sort of thing. Or you can work with an outsourced photogrammetrist. Big just spoiler alert that shout out to Aerotos. That's what we do. We're a team of photogrammetrists and CAD technicians. We love processing data. So if you want, please process your data through us as well. But when it comes to photogrammetry, all of these different softwares, again, like a lot of softwares, we've seen a lot of just kind of merging together that they're all very similar. They're becoming a lot more similar because the industry has realized what's good and what isn't. There are definitely differences in their architecture and their user interface. Some are much more detailed, some are much more user-friendly. We actually use Pix4D as our primary photogrammetry engine, but the software is not going to just fix photogrammetry problems for you. It's really about the workflow, how you run photogrammetry. Once you get that field data in or the GPS data from the other talk, that the photogrammetry is more about managing time and workflow than it is about just getting the right computer or the right software. Any questions about photogrammetry or anything on the technical side there that I may not have answered? Cool. Well, then let's start talking about LiDAR processing next. So LiDAR is going to be a little different than photogrammetry. Photogrammetry, like I said, photogrammetry software, you can use basically any image and put it into any photogrammetry software. LiDAR processing is not that way, at least not at the beginning. So creating the actual point cloud itself, for those of you that aren't familiar, LiDAR itself, a LiDAR sensor is not like a camera. A camera shoots a photo and what you get back is the photo. That's what comes off of the camera. A LiDAR sensor, it shoots out hundreds of thousands of laser pulses per second, and all the LiDAR sensor itself, measures is the distance between the LiDAR sensor and the pulse on the ground. And it's huge amounts of data of hundreds of millions of those individual pulses. They're not in a point cloud yet. To actually create it into a point cloud, you need to combine it with the IMU on the drone, the GPS or GNSS data from the drone itself, and often with the imagery that was taken on the drone as well to colorize it and actually create a usable point cloud. Because yeah, like I said, the laser itself only records the distance and it's a lot of data, combining with all of that before you actually get to a point cloud. And this step is almost always going to be controlled by the LiDAR manufacturer. If you are flying a DJI L1, you have to put that first step through DJI's Terra software. If you are going to be flying like one of the Rock Robotics drones, you have to use their software to actually create the point cloud. Now, once you get to that LAS point cloud, you can work with that in whatever software you want, and I'll talk about those softwares in just a minute. But the first step of actually creating and georeferencing that initial point cloud, getting it into the right coordinate system, is almost always going to be controlled by the drone LiDAR manufacturer. And this is another one of those steps where it really, really matters what drone you choose then, because sometimes even if the drone is great, if their software support is really crappy and you have to go through their software, that can be a big pain in the butt. So it's worth actually looking, if you're interested in buying a LiDAR drone from a manufacturer, it's worth looking on YouTube for the videos of how to process their LiDAR data. That can be very informative, I've seen. If it's a 20-minute technical YouTube video for just how to create an LAS file, that's a big red flag for someone like me. Creating the LAS file should not be taking you 20 minutes of tutorials to know how. It should be much simpler than that. But yeah, it is in the background. All of these are doing the same thing. They are combining the GPS data, the base station data, the IMU data, the imagery data to actually create that single point cloud. Once you're there, depending on which LiDAR system you use and how you georeference it, you may also need to do a swath-to-swath alignment. This is based on a number of different factors, what type of GPS post-processing you do, because sometimes raw LiDAR clouds can look like this, where this is an exaggerated version, of course, but where a house on different flights might be slightly offset and you want to combine them together, that's pretty easy to do. Georeferencing your point cloud, that can be a little bit more tricky, especially with LiDAR, depending on how you're georeferencing it. Because this one right here, I don't know why I spent the time capturing these photos. I promise you, these are actually the same exact point on the ground, even though that one is literally just a set of black points. This is going to be a photogrammetry colorized point cloud, and this is what the raw LiDAR point cloud looks like when colorized by elevation, because it's relatively flat. It makes horizontal georeferencing with point clouds kind of tricky. Now, there are a couple of ways to do that. You can colorize the point cloud based on intensity. That's one of the background ways that you can actually still see you can see the ground targets. You can use a colorized LiDAR point cloud for 2D geolocation or for X and Y georeferencing. That is often not great because the colorization of a point cloud is applied typically after the fact. So it's not, the colorization on a point cloud is not nearly as accurate in 2D as most people want it to be. Or you can do a lot of this with GPS post-processing. So there are a number of ways to do it, but either way, we really like using ground control points in general. And I mentioned this in the GPS workflow yesterday. Part of why we like using ground control points so much is that they are simple, reliable, cheap, and verifying too. Ground control points with LiDAR even, yes, it can be challenging to georeference in 2D, but oftentimes you have to, right? I mean, the number of survey projects that are absolute, true, pure NAD 83, there aren't a ton of them. Usually you localize over a point on a site because, well, hell, this is California. The ground itself, well, this isn't California, but California. In California or in any mountainous region, the ground itself can move. So if you're trying to do a survey that actually matches up with the existing monuments, it might be a few tenths of a foot in a different direction than it was 10 years ago when it was last surveyed. And so you just localize over a site, over a known point, and that's easy. And the best way to do that is with ground control points. So we really, really like ground control points, especially because for surveyors, you're going to be on the ground anyway with the tools and ability to measure it. So taking ground control points is a very small, marginal additional step to get a huge amount of workflow reliability, of accuracy, of actually having that known data. It just makes it that reliable workflow that's so much more resilient to the real world stuff that can happen. I was talking here about georeferencing point cloud. Like I said, LiDAR hardware often relies on GNSS or IMU processing alone. Integrating those ground control points will help you localize your point cloud and also, again, find errors if your LiDAR sensor isn't properly calibrated, et cetera, et cetera. There absolutely are ways to georeference your point cloud properly. And the other thing is that actually lets you still use a LiDAR sensor even in completely assumed datums, right? If you shot your ground control or your sites on a 5,000 by 5,000 grid, you can actually still do that perfectly fine and still use LiDAR data great, even on a 5,000 grid with just using ground control points. It's the simplest way to get there. So from there, at this stage in the process, we have created our point clouds, right? We have a photogrammetry point cloud and we have a LiDAR point cloud. We haven't done any drafting yet, right? We haven't created a tin surface. We haven't vectorized it. We haven't drawn any curb lines or anything like that. The next step is actually measuring and certifying accuracy. And this is really, really important, again, to do it at this stage of the process because it prevents you from finding out that your data is bad later down the line. Data is bad sometimes because, again, this is the real world, right? Sometimes it's bad because people shot their control wrong. Sometimes it's bad because the data just broke for some reason. Sometimes it's bad because we've seen one where a big bug hit like the image sensor at some point and caused some aberrations in the imagery and just like caused a bunch of weird results in the end data. We've seen all kinds of weird things that aren't like your workflow, it's bad, but you want to catch these errors as soon as humanly possible. So to get to survey grade accuracy, as we measure and certify accuracy, I start by talking about what it means to actually be survey grade accuracy. Well, there actually is no single definition of survey grade. In fact, if you think about what survey grade means, there were surveys done hundreds of years ago where if it was 10 feet accurate, that was actually really, really good, especially when they're surveying, entire mountain ranges 100 years ago, it was a survey point, and they say, yeah, it's plus or minus 10 feet, and that would be considered really good. That was survey grade. So there is no definition of, oh, survey grade must mean 1/10 of a foot or better, or 2/10 of a foot or better. Rather, what really matters is knowing what your accuracy is and being able to state what your accuracy is so that it is good enough for the end use case of whatever it's being used for. There are different ways to even measure accuracy too. Some older ways are going to be things like the National Map Accuracy Standards. Those were used for a very long time and were very, very good for government maps for decades. Using a 95% confidence interval, it was when we started to shift more as an industry towards statistical measures of that sort of thing. Things like the RMSE, or root mean squared error, of your ground control points has become very common, partly because it is what is used on the top line of a Pix4D quality report. It's worth noting the RMSE of your ground control points can very often be misleading. That tells you the internal error of the points that were used to georeference the project. So it's almost always very low. In fact, you can often see projects where the reported error of the ground control points themselves is on the order of a few thousandths of a foot, which is obviously ridiculous. Drones are not capable of a few thousandths of a foot. But what is now the new gold standard for accuracy is the root mean squared error of independent check shots. And the way to actually measure that, I think I have it here, is a document called the ASPRS Positional Accuracy Standards. ASPRS is a nonprofit, very academic organization that publishes these free-to-use, publicly available standards for actually measuring and certifying accuracy. Now, I won't go into all the details here because, again, it's a 20, 30-page document, but yeah, question? Yeah, so a 95% confidence interval was a way of stating that we have a 95% confidence that any one point on this map will be within half a foot accuracy, for example. So if you said it's half a foot accurate, the accuracy statement might be any individual point. If you pick individual points on this project, we guarantee that at least 95% of them will be within half a foot of where the actual measured is if you were to measure it again on the ground with a different set of tools. 95% confidence intervals are, like I said, it was a very common way to evaluate accuracy. Evaluating accuracy is very challenging for a lot of people because we're getting into the world of probability and statistics. And that's a world that, honestly, I live and breathe in. That's my formal education is in statistics. So this is like something that I've been working on my entire life. But people really want to know, well, is it accurate or is it not? But in the realm of this sort of data processing where you're working with such insane amounts of data, you can't actually say definitively, this point is accurate and this point isn't. What you rather, the way that we have to say it is, well, there's a 95% chance that it's accurate within this level. It's kind of this, weird world of probabilities of what individual points are and how accurate they are. And 95% confidence interval was a way of saying that 95% of these points of check shots are going to be within a certain amount. The reason why it wasn't great is because that 5% of points that might be out of tolerance would then potentially be out of tolerance by a really, really big amount, where you have most of your topo is fine, and then you have this whole area that's off by 3 feet, and that can be enough to cause massive, massive problems. And that's where this new, again, it's very statistical, so it's hard for a lot of people to have this probabilistic accuracy. The root mean squared error of independent check shots, the latest and greatest certifications for these are where you can estimate the true probabilistic error of check shots based on information like the camera calibration and the GPS data and what the amount of error in the GPS when compared to the photogrammetry, when compared to the LiDAR. Comparing all of these figures, you can actually create a statistical assumed accuracy based on that new model. And if you want to learn more, honestly, this is the document that actually tells it. These ASPRS positional accuracy standards, they're getting reworked this year, which is really, really cool to actually make them even more accessible, I think. Right now, it's very academic. I've seen the draft of the newer version. It's Still very academic, but a little bit less so. They do a lot better of actually defining their terms in the new versions. But this actually tells you all the way down to the actual math, the formulas that are used to actually create these root mean squared errors. And it allows you to create these accuracy certifications. These will also be updated in the new 2023 versions as well. But there are there are basically two different tiers of accuracy certifications. There's one that's called a tested to meet certification, and another that's a produced to meet certification for accuracy. The produced to meet certification is the lower tier. It is not as stringent of requirements to get to that because it is based on photogrammetrist judgment, the actual technician that uses it, their experience, saying, based on our experience and the other data, we believe that this is an accuracy class of X centimeters root mean squared error. And the tested to meet is the higher standard. That's where you follow a very, very, very robust series of testing your data with independent check shots. So that means you would be setting check shots. You would not be giving your check shots to the photogrammetrist or to the LiDAR tech that's creating it. And then you bring those check shots in after they've created the point cloud and say, all right, how close is their point cloud to these check shots that I didn't even give them? And that is what is required, these independent check shots. That's what's required to hit that tested to meet standard. That's the highest standard that you can get. That's what's going to be required on a lot of very high-end government jobs where they're willing to spend to get all of those tests. Yeah. Great question. Tested to meet standard is 20. I think that's when they're considering increasing it to 25 on the newest ones. I don't quote me on that, but 20 independent check shots that are well distributed over a project is statistically proven to be statistically significant to actually report on the true error of a project. That's where you get into the real analytical and academic world of statistics. So that highest tier of tested accuracy it remains 20 check shots. Now, in the real world, 20 check shots takes a good chunk of work to take an additional 20 check shots and make sure they're well distributed. I can tell you from personal experience, the overwhelming majority of projects do not hit that highest tested to meet standard. Instead, they go for a produced to meet standard. Produced to meet standard can theoretically be done with 0 check shots whatsoever. However, most surveyors in our experience usually keep a couple of check shots, 3 to 5 check shots, something like that, that they use to test the final model against their photogrammetrist data just to be sure. And that's still going to be enough to give a produced to meet, and it'll give them a little bit higher confidence even than the produced to meet standard because, yeah, we tested it with check shots. It's not enough to give it the full tested to meet certification or anything like that, but we did want to make sure that we actually test our data. And that's a very responsible and good way to do it. So moving on from accuracy standards and all of that, by the way, if you want a copy of these ASPRS positional accuracy standards, shoot me an email, just logan@aerotos.com. I'll have my email address at the end. We'd be more than happy to just send the PDF along because we like the ASPRS nonprofit organization. Honestly, if you're looking to learn more about photogrammetry, the ASPRS is the right place to start. My only possible criticism of them is that they are extremely academic to a fault. And they oftentimes say like, yeah, so what's it matter if you have to spend 40 hours in a lab reading a textbook to actually get something done, where surveyors want to actually get work done, but their academic credentials are very, very top notch. So we like that. All right, so now that we've verified accuracy, it's time to actually extract data from that. Line work drafting, as well as with LiDAR more, one of the biggest things that is becoming more and more time consuming, like I said, as LiDAR remains very popular, everyone's talking about it, is point cloud classification. So that means things like power lines, buildings, objects, vegetation, actually classifying it into all of these things. The first step that you need to ask yourself is it worth the time to classify your point clouds? Being in the booth in the exhibit hall and talking to people, some people said, oh, you do data processing for surveyors. I say, yeah, that's what we do. And they're like, oh, can you do a classified point cloud? And I'm like, Well, yeah, we can, but is that actually what you want? Rarely do people want a deliverable as a classified point cloud. They are only using it as an intermediate step to actually get to the terrain. So when it comes to point cloud classifications, this site is a fully classified power transmission line where you have transmission power lines, distribution lines, low vegetation, high vegetation, and ground all individually classified. Most survey projects don't care about that. If you take the time to differentiate the shield wire from the actual transmission lines, that doesn't matter for a surveyor. They care about only two classes most of the time, ground and not ground. And that's it. And that's usually enough for most LiDAR projects. And even then, a lot of times people spend time classifying ground and non-ground when they wouldn't use the LiDAR data at all. They'll be gathering it from photogrammetry data or from the ground. So they waste all this time separating the building out from the ground when they're not even going to use that in their final surface. So the first step before you even start classifying LiDAR point clouds is ask yourself, is it worth the time? Do you actually need to classify it? And asking things like, what classes do you actually need? Ground, road, bridges, noise, low, high, medium vegetation, buildings, poles, lines, snow, all of that. All of these different things. There are projects where the difference between road and dirt actually matters, and you need to classify road and dirt differently. But the majority of projects, in the point cloud stage at least, road and dirt is all ground. Trees and buildings are all not ground, and that's enough. Yeah. Great question. LiDAR, 100% LiDAR. For power line mapping, LiDAR is really the only option. Photogrammetry is not capable of reliably collecting power line data. Exactly. Photogrammetry requires 3D matches, and power lines are 2D lines. So they are, I don't want to say impossible, but yeah, it's effectively impossible to do photogrammetry to create power lines. You need LiDAR. Actually, yeah, that's a good point. I really should add it to the slides. It's vegetation or power line. And power line mapping is its own kind of niche thing. For example, if you are doing that, your guys probably use PLS-CAD or some sort of similar power line survey program. And that's where you absolutely do need this sort of classification, because the rules are different as far as how far I'm going to say something stupid because I don't know power lines that well. 240 volt line or something, how many feet that can be away from a building, and how many feet that can be away from vegetation, and how many feet that can be away from another object or from a road is very, very much matters. And that's where classifying this level of classification. In fact, this was a survey that we did for a power line company that really, really mattered. And the distances from this line to that line really, really matters as well. So when you are doing that, it does have to be LiDAR, and you do really care about classifications. So how do you actually classify it then? Well, what software do you use? This is one where a lot of people, like with photogrammetry, Pix4D is the market leader. Point cloud classification, there is no real market leader on this. A lot of people say, what's the best software for point cloud classification? And what we've found is we have licenses to most of these things. There is no magic bullet. Some are better than others. They all kind of have trade-offs. They have all of these different great tools, but they're kind of a clunky user interface. Some have a really smooth user interface and that sort of thing, but maybe they don't have as many tools for doing, path profile views and extracting lines and surfaces in different ways. Some are really good at their automatic ground classification algorithms, and others are better at their power line classification algorithms and that sort of thing. But generally speaking, our recommendation is just to use what you're most comfortable with. If you are entirely in the Leica system and you already use Leica Cyclone, then yeah, it's going to be good enough. It's not perfect. I don't particularly like it, but we have some LiDAR techs that absolutely swear by it. Global Mapper is kind of a GIS-based one It really is a jack of all trades that can do a lot of things, but it's not going to be the fastest when it comes to large, very large point clouds. It can struggle with that sort of data. It's not the most advanced one out there, but it can handle all kinds of different data formats. Yeah, these are some of the most popular ones that are out there, but really they're not all that great. Trimble Business Center is probably the weirdest one. That software tries to do absolutely everything, but some people swear by it. So okay. Another question in LiDAR is whether or not to thin your point clouds as well. Remember we were talking before about I've never had someone say this point cloud isn't dense enough with drone LiDAR, but I have heard lots and lots of people say on the data processing side, this point cloud is way the hell too dense. There are too many points, and it's a pain in the ass to try and get everything out of it. And that's often very true. Many projects can very easily exceed 1 billion points and multiple billions of points. And so one of the ways to get around that is to actually thin your point cloud. This is one where there's a lot of research still being done, including by us, of the proper ways to thin a point cloud without either losing accuracy or accidentally introducing new errors into a software or into the surface. Because there are a couple different methodologies for actually thinning a point cloud. The simplest is one that we would call dumb decimation, where you basically every 9 out of every 10 points you just delete fully at random. And that's not actually a terrible way to do it, because by using that something that's completely random, it's statistically going to not introduce any new bias into the data set. If you have so much data that you can delete 90% of it and still actually see the ground clearly, that's a very statistically robust way to do it, but you are losing a lot of your detail, especially on like curb lines. You might lose some of your detail there on power lines. The other ways that are quote unquote smarter ways to thin a point cloud takes denser areas, so like the areas that are dense with the tops of the trees here, and remove a whole bunch of points so you only have a few left. And areas that are not as dense, where it only took a few branches, it'll keep most of those points. That has the challenge of oftentimes introducing new biases and errors into the ground because of the way that it actually creates individual 3D cells and then only puts 1 point per 3D cell or something like that. It can actually, if you look really closely, it's hard to see on this data set, but when the ground, if you look at the average of the blue line, the full resolution data set, you'll actually notice the red one, which is the thinned data set, is actually a little bit choppier. It has higher highs and lower lows because of the way that the intelligent 3D thinning model actually introduced a bias into the data. So this one where thinning point clouds to make the data easier to process is viable, but you have to be very, 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 very careful that you are not introducing new statistical biases into your data. From there, like we've talked about, you kind of classify and filter it, remove your vegetation. Also, another thing to be aware of is just acknowledging the fact that LiDAR penetration is not perfect, like we talked about before. There are gaps in here. Depending on what ground classification methodology you use, and different softwares, they all have their own ways of setting it, how wide of a gap, how wide of a hole you can have without ground data. Sometimes they'll see this gap and assume, oh, there's something there. So it calls like the lowest points on this bush ground. And then your ground surface has a big, spike here is something that's very common in ground classification algorithms. So making sure that you have a human being to QA a lot of this is pretty important, because a human can often look at that and say, look at the imagery and say, oh, there's a big boulder there that actually probably would be a high point in the ground to show it as a rock. Or that's just a dense bush, and you do then go interpolate directly underneath it. So making sure that just acknowledging imperfections in the data, because again, we work in the real world, data is totally imperfect. So once you classify it, our next step typically in LiDAR is actually to create things into a digital elevation model as well. I'm pretty sure I have some slides in a bit of exactly how to do it and why we like converting LiDAR ground data at least back into a rasterized DEM. We'll cover that in just a second. But one last thing on that ground classification is, honestly, part of why automatic ground classification programs still have a ways to go is because there's so much human judgment that's required on what even counts as ground. For example, if you see a big debris pile like this, there is a use case, or there is an argument to be made that, yeah, that's ground. It's a bunch of chopped up concrete. That's basically a little concrete hill. Alternatively, there's a way to say, no, that's a stockpile or that's debris. We're going to be clearing it. The actual ground surface would go underneath it. Likewise, with major stockpiles like this, is the actual quote unquote ground surface going to be the top of this stockpile or the bottom of this stockpile? And the stockpile itself is classified and measured differently as a stockpile. There are very good arguments and good use cases for both of those things depending on the actual survey. And same thing with rocks as well, right? Is that ground by itself, or are those rock outcroppings that are marked separately? There are reasonable arguments to be made for both. And the human judgment is, could you even tell what all of these are if it were underneath trees and you didn't have the images? A great one that I should put a picture of on here that is different between humans and automated things is if you ever see the profile of a car underneath a tree. If you had a car parked underneath a tree, a human can look at the profile of that in pretty much any way in LiDAR data and say, that is obviously a car that is parked under this tree. I can see that there is a road going under this as well. So that is clearly not ground, and you just ignore it. Whereas a automated machine would say, oh, that looks like a hill to me. It's a lump, it goes up, it's not at crazy steep angles necessarily. It's just a 3 or 4 or 5 foot tall hill, and that's what an automatic ground classification will do. So we like a lot of these automated ground classification softwares. They are great, but they pretty much all require a certain level of human judgment to clean it up and get that final information as well. From there, like I said, we actually rasterize the point cloud data too after we classify it before we finally get into the final surface. And part of the reason we do this is aerial LiDAR point clouds are, as I said, clouds. They are not perfect individual points. This is one of the coolest parts of the workflow to me as like the mathematical statistical guy that I am. This is what a profile view of a point cloud looks like. And if you look here, this is the top-down view. You can see this is a profile view of a road. So it starts here, kind of goes down, and then it goes up towards the crown of the road, just so you can see in the profile view. Now that's concrete. There's no vegetation, or it's asphalt. There's no vegetation. That should be a pretty hard surface. But what we actually see here is a cloud. There's actually a good amount of noise in that data. This is the reason why a lot of people say, oh, I don't like the L1, or maybe I want these other systems because there's noise in the data. And while each individual point on this point cloud may have half a foot of noise or accuracy on each individual point, the average of these points is statistically proven to be far, far, far more accurate than any point individually. Take the human eye again, is really able to see this. You'd be able to draw a line that goes down the kind of weighted average of this, and it would be smooth. And the data very much bears the fact that that line, that average of all of these points, is going to be really, really, really a lot more accurate than trying to take individual points out of the point cloud. And this is where your LiDAR processing workflow really matters. Because if you just extract individual LiDAR points from your LiDAR point cloud in order to create a surface, then you are getting this much error. You might see half a foot of error. But if you are rasterizing your data, you're averaging those points, you're going to get a lot better data. So what is raster data? That's basically taking the point cloud, the vector data, and turning it into raster data. Raster data is going to be a grid. A picture, for example, is a raster data set because it is all pixels. It's the number of pixels in the grid, and it is rasterized and that sort of thing. A little bit more simplified. This is the difference between vector data, which is going to be exact lines, and this is what it looks like in raster data. Obviously, we're working at much higher resolution, so we're not actually gridding everything to the point where you're losing any meaningful details. To show you what it actually looks like, again, on this point cloud, this is what that raw point cloud would look like. Again, another profile view. This one has some low vegetation as well. So you have this ground data, and when you rasterize it, when you create what are often called bins in the post-processing side of things, and you average those individual ground points within a bin, depending on how big you make it, this might be what a really tight-looking raster looks like. And what you can see is there's a whole bunch of noise there. but it's already smoothing it out. And then when you get it dialed in right, this is what that surface will look like after you rasterize your data. And if you look at that surface, this is again where the statistics actually matter. This is how you get your 1 to 2/10 of a foot accuracy off of LiDAR. The actual laser scanner itself has so much noise from other sources that typically you do need to rasterize your data to get that really, really smooth data. The other thing that's worth noting is if you look at the scale of this too, what we're looking at, this is 2.5 feet, this is 5 feet, so this is a distance of 2.5 feet, and there are probably 40 or 50 points in there already. And this is a very, very narrow width band that it's looking at. There's a lot of data to average this out. So even when you're doing topo on a 1 foot style grid, there's a lot of data. And what that winds up looking like is this would be the imagery of a real project that we did. We went through all this classification, the rasterization, and this is what the same site looks like rasterized from an elevation model. What you can actually see is not only is the creek bed really, really obvious, you can see things like fallen trees are actually very visible as well. And even the ruts made from tires in the tire track, you still actually are preserving that level of detail even when you rasterize your data. This is what a raster data set looks like. See some other interesting things like these little cones are actually the base of a tree as it slightly goes up to a tree before we then cut it off and classified it as vegetation. That's even easier to see here. We have some of those different color differences. So that's kind of LiDAR drafting in a nutshell. And to finish things off, we are going to talk about line work drafting. So line work drafting is when you take these full resolution, these rich 3D models, and you actually simplify and reduce them to a CAD-friendly surface. And that's because, well, photogrammetry outputs and LiDAR outputs both are honestly, they're just way too big for CAD. You need to reduce them to CAD compatibility before you can put it in Civil 3D. I promise you, Civil 3D cannot process a billion point cloud. It also can't do a 10 gigabyte or even a 5 gigabyte ortho photo. And even if it could, drafting in Civil 3D is kind of a pain in the butt. So why is line work drafting necessary? A couple of reasons. One, the files are just way too big, too much data that you don't need, right? These full resolution point clouds have a huge amount of data on the trees. You don't really, yes, trees matter. Sometimes you need to mark exactly where the trees are, but you don't need to know where every single leaf is. Also, the full resolution data often has things like ugly contours, right? That you're going to have contours drawn over building, vegetation, or cars, things like that, that you need to figure it out. When you are drafting, the first question that you should really ask yourself is whether you're drafting with LiDAR or photogrammetry. Like I mentioned before, if it's vegetation and you have LiDAR data, take that out of the LiDAR data. If it's hardscape, you should probably take it in photogrammetry. This is another just interesting example of LiDAR that shows that the LiDAR system used here is in yellow, actually has a little bit higher spread than the photogrammetry data. Now, again, you can rasterize this and actually get better LiDAR out of it. But in hardscape, again, all of the research studies we've done will show that photogrammetry data on things like this, on a roof line, the photogrammetry data is going to be more accurate. When it comes to actual line work drafting software, because that's the next question, which software do you use? Here are a handful of softwares that you actually can use. Much like, well, honestly, photogrammetry and LiDAR processing as well, there's no magic bullet with this, at least not yet. There's some really cool companies out there that are trying to get machine learning to automate drafting. They can do a lot of things that are very cool. They're not quite there yet. I think they're going to be pretty close, but I've also heard a lot of times that technology is very close and it's not quite there. But at least for the today answer, maybe this will be different in a year. For the today answer, there are things in here that can automate certain parts and they can help you draft brake lines and they can help you find power poles and power lines. But usually it's pretty manual because line work drafting takes a lot of time. It doesn't take much computer time. This does not require powerful computers at all, but it does take a lot of human time to actually draft this. And not even very skilled labor is required to do this. It's a lot of like entry-level CAD techs. So we honestly discourage a lot of surveyors from doing their own drafting just because, I mean, if you're used to billing out, you know, north of $100 an hour or something, then that's your time is probably better spent in the field doing something that isn't tracing paint stripes in, you know, a parking lot of a strip mall or something like that. But line work drafting, it's still a fairly manual process, and there are no magic solutions out there. That said, there are different options for line work drafting as well. There are automated softwares out there that will try and pick all of your key points and all of your utility access panels and manholes and draft your brake lines. They are cheap at scale and very fast. We have found in practice that they are not great for survey just because they're not good enough. They don't, if they get 90% of the utilities, that's good, but you can't deliver a survey and say, don't worry, 90% of the stuff on the site is marked. That's not how the survey works. You can do the drafting in-house yourself with one of the softwares I just had up on the screen. It's going to be high accuracy, reliable, well-known product, but you typically have very expensive labor. It's time-consuming. You aren't specialized, or you hire a photogrammetrist. It's again, shameless plug for Aerotos as well. This is the type of work that we do. We have our photogrammetrists, and then we have our drafting team. But this is what we do all day, every day. And to answer, I mean, from this, people say, "Oh, well, what software do you use? Do you have any magic bullets?" And the answer is, no, we don't. We just like to think the only reason people work with us is because we've learned the workflows that are really, really efficient. It's what we do all day, every day, and we have really good procedures and standards and workflows to actually get the data in and out reliably, accurately, and quickly. Part of that good workflow is even having just very defined drafting standards. This is where things come in. And again, the human element still has a major advantage over the automated element when it comes to things like, how do you draw a sidewalk with very significant damage? Do you draw it directly along the sidewalk line, or do you try and trace it along where the damaged parts of the sidewalk are? Computers and machine learning oftentimes do both. Well, it's a hard judgment call, but humans, a lot of times, I can actually tell you the answer for us. We have standards of how many feet there has to be of cracked or damaged sidewalk before we mark it specifically as cracked or damaged. But also just having a straight line with the imagery backing it in a CAD file is typically one of the best ways to do it so that you can actually see it. Same thing with what are the density of the topo points used to create your tin surface? How do you balance that? How big and usable the files are versus how much resolution and granularity we get into it. Drawing curb lines. How many curb lines do you draw? 1, 2, 3, or 4. Back of curb, top of curb, gutter, flow line, edge of pavement, things like that. And also even interpolating under trees. Having clearly defined standards is what makes the drafting workflow a lot faster.